and to determine if that object is applicable using Boolean reasoning, then finding that object, bringing it to a certain target location, for instance, to a user. And then it would be good if it would know where that user is, if it has previously seen it. So all these technologies come together. It remembers where the object has been based on the semantic mapping ability. And of course, it needs to be able to perceive the object in order even to grasp it. But this is the functionality of the actuator arm. Essentially, if you have some arm attached to the robot and you want the robot to be able to pick up an object using that arm. And that by itself is a difficult problem in the robotics community. It's called manipulation. Object manipulation is a very hard task. And but there are some established components, ROS nodes, which can help with that, like MoveIt2, which we use. That is designed to help with that by providing some functionalities like motion planning or inverse kinematics. Essentially, if you imagine you want the robot arm to reach a certain target location, like there's the object, you want the arm to reach that, then ideally you would want that arm to move towards the target, but while not hitting an obstacle. So it needs to plan its motion, essentially. So we need some form of motion planning to do that. And in order for motion planning to work, it needs some form of inverse kinematics. It needs to know how long the joints are and what are the min and max angles, so that it can take into account how it can move its arm and where the end location of the arm, like my fingers, will be after moving my elbow or my shoulder. And so it takes all this into account for successful motion planning. And this is integrated with our semantic mapping capabilities. So it knows when it sees an object, where the object is relative to each other, so that it can then grasp it using this motion planning ability. And then the reasoning can take over again and for instance, determine where to bring that object to once it has been picked up. The overall architecture looks like this. There are essentially multiple ROS nodes involved. We try to logically group this into different functionalities which have to be performed, like this perception node, which runs the deep neural network, then the semantic mapping and localization, which is also tied to the navigation capabilities, and also additionally this meta bridge, which allows the use of the mobile robot, controlling the mobile robot from metacode. And here we now see an example of that fully integrated system with Boolean reasoning, searching for an object to bring to the user. It's basically instructed to bring a toy to a human. It doesn't yet know where the toy is. It doesn't yet know what object might qualify as a toy. It doesn't yet know where the human is. So it starts to explore the environment, as you can see here. And then it encounters this orange object, which is initially classified as an orange. It has some knowledge. It sees this thing is round, then does some abductive reasoning. Balls are round, oranges are round. Infers that maybe the orange can be taken as a toy, essentially. So it determines to pick up the orange and to bring it to the human. So now it's busy with the next step, which is picking up the orange, which by itself is not an easy subtask. But you see it's approaching the orange and it's trying to pick it up. And here you also see the semantic map, where in green you see where it thinks itself to be. In red, it seems it has already seen the human over there. So it already knows there's a human over there. And you see it has picked it up and now it wants to bring the orange to the human. So it seems like it will succeed, but unfortunately the physics don't want it to succeed. You will see the object slips out of the actuator. Slowly, but slowly at first. Now it's for problem. So it's here, you see it. planning and execution is not the final answer. Often reality does not allow your plan to succeed right away. So the now reasoning system, PLN reasoning takes over again. It figures out there's no object in the actuator, figures out I still want to bring the orange to the human, so invokes the action again to pick up the orange. So it picked it up again and continues to bring it to the human. And oh, it slipped again. But you see here this importance of taking real-time perception into account, because the object, how to say, there can always be things that go wrong during the mission. And in order to make the behavior of the robot robust, it needs to take this real-time perception into account so that it can adjust to these disturbances, so that it can essentially correct its mistakes and find a way to make it work. And you see here, it's again adjusting itself and trying to pick the orange. And what's quite interesting in this particular simulation, we intentionally put the fraction of the orange to a very low value so that it would repeatedly slip out, so that we could essentially test how robust is this capability. Yes, and now it essentially serves as a quite interesting demo, and also as a test bed, because it's now very easy. I can show you the metacode for this. It's very easy to incorporate your own metacode and your own AI code to drive the behavior of this robot. And yes, here it slipped out again, and now you will see it's one last time it will pick it up, and because it's moving a bit, one last time it will deliver it, but it's already pretty much there. So the takeaway here is we have a full integration of probabilistic reasoning with the robotics pipeline, with all the ROS2 nodes which we have developed, which allows autonomous robots to be controlled by metacode, incorporating probabilistic logic network reasoning. So that's what we have here. And yes, ideally, let's see. Yes. Yes, I think it works okay here. Oh,
Just a quick question. What is SLAM? It's the acronym.
Simultaneous localization and mapping. And the idea is for the robot, if it's in the environment, that it automatically builds a map of the environment while it's observing it. So it needs the reason why it needs the map is also to localize itself, to know where it is in the environment. So it's essentially a combination of mapping and localizing itself in that map it built, so that it has a rich environment representation. And I will show some of the, I'm not sure how much time I have left.
Wrap as quickly as possible.
Then I will only very quickly show only 1 minute.
Thank you so much.
Uh-huh.
I apologize.
Thank you. And the way you see this, maybe. I hope now it's big enough. So you see here in the knowledge base of PLN, we can define different objects, and we can also describe different categories, like category of a toy. For instance, frisbee is a toy, sports bar is a toy, and we can also add additional attributes like oranges are round, sports bar is round with various truth values. So you can essentially describe some common sense knowledge about the object. And that's in the demo, it was important because when it saw the orange, it doesn't have information that the orange is a toy, but it has information that the orange is round, and it knows the sports bar is a toy. So sports bar is round, orange is round, sports bar is a toy. So maybe orange is also a toy. And so there are already two inference steps involved here. One is to relate the toy to the spot spur, and then to know this spot spur is a toy. So orange is also a toy with deduction. This case, so one abductive step and one deductive. And you see this, so you can essentially define knowledge using BLN, but you can also have some dynamic knowledge from observation. Like here, you see there's one BLN statement that is fed in from the observations the robot makes. So if it sees the orange, it explicitly creates the statement that the orange is an object that is currently seen, essentially, so that it can then apply the other, combine this piece of information with the other, like is a toy currently seen. So it can combine this dynamic part of the corresponding to current observations with the more static parts that correspond to the knowledge in the knowledge base that are known about the different objects. And then you can simply have like here it's essentially like a behavior tree which the robot uses. Essentially, if the idea is in each step you call in each robot cycle you call the step function, and then you end up in one of the leaves of that behavior tree. For instance, if there's no object in sight, it just goes to unknown locations in order to find objects. And additionally, if it, for instance, already has seen an object and and according to PLN, it's an object that should be picked up, then it will end up here in the tree, calling the, where is it? The big operation exactly here. So you see there are like different nodes in that behavior tree, but the conditions are invoking PLN reasoning to determine if that object is actually the object it should bring to the user. That's very easily adjustable metacode that can be extended to run your own AI codes here. Yes, that's basically all.
And in the interest of time, I think we better move directly over to Matt with attention.
Hey, while Matt is setting up, can I show one thing?
Yes,
1 minute.
1 minute.
1 minute.
1 minute.
The question is. Yeah.
Thanks.
Log in
Yeah.
to multi, that's the only question. Perhaps the answer is. So.
Guys, just end here. I want to keep going.
Am I getting let into Zoom or am I getting let into Zoom?
Yes, there you go.
That one is yes. So
1 minute and a little bit of a black hole.
No, wait 1 minute. All right.
It's already this.
No. I mean, like from the moment I start presenting.
There's no defined record trade. 1 minute and something for sure.
All right, folks. Real quick. So, like, when I presented earlier, right, I said like, hey, there are only a couple of line changes to make this actually multi-processing across machines. I made those couple of line changes. So it was exactly what I thought it would be, and we can now observe it actually working. So we can say something, we are doing this task single-threaded. We run the orchestrator, so it will run across 2 machines, and it takes a while. Like now it's dispatched, and it takes a while. We are talking and wasting our like 1 minute of time. But it's worth it. Like we will get the results. All right, processed. Now we check that we have 1024 to the power of 2 results. That is single-threaded because we are counting and Python is slow. Yes, okay, so we have that many results on machine 1. Now we are counting the results on machine 2. Yes, all right, cool. Yes, but let's now do this with 8 threads per machine. And it's dispatched, and don't make me lie, and it's processed. All right. So yes, 8 times as fast. And I will be pushing that to GitHub so you can actually run it for yourself.
Yeah, very, very exciting to see so much stuff actually working, right? And there's more of that each year and each couple months now, even, which is really quite fun. And in terms of PLN, I mean, we've been playing with different versions of PLN on a research level for a while. I think the 0.5 release is a big step toward making it more systematic, and as we move from 1.0, it's going to get even more comprehensive in terms of embodying more and more of the PLN theory that we've been developing for a while, and we'll shift from metamorph onto the meta IO route and then make it even more scalable. So now Matt and I, for the next bit of this, are going to talk about some other stuff that's in the works and has been prototyped in OpenCog Classic, and we've written a bunch of research papers on it, and we're now gearing up to make large-scale implementations of these things in Hyperon. So Matt will cover attention allocation, and I'll talk about program evolution and motivation.
Okay, so I'm going to be in the framework of nil and try to save a few minutes here and there. To begin with, attention is, as Ben mentioned, is one of the primary pieces, along with uncertain inference, evolutionary learning methods, and other AGI cognitive modules. And in a sense, a lot of this has to do with how does everything begin to come together. So one of the core pieces, along with some foreshadowing for this afternoon. So attention, first of all, I've broken this down. It's going to be fairly quick. I'm going to talk about very briefly, go over kind of our original approach in OpenCog Classic, which actually goes back quite a bit further in time to some ideas prior. I'm going to talk about a deep funding result that we've come across, which is that was funded, which is the Synapse framework by Simuli for evaluating different attention systems and how that's going to help us move forward in time. And then same with some ideas from predictive coding and how attention can inform us, and how some of those ideas can inform us on future iterations of attention systems, along with thinking through what are really the ideas we need attention to help us solve within this context of the Primus system. And I'm going to finish with a very kind of iterative process in how we're thinking of getting towards that goal. So I'm going to start off with a very brief summary of the system we used in OpenCog Classic, which was called Economic Attention Networks, or ECAN for short. It's a system that simultaneously stores some memories, but it also allocates resources in AGI systems. It is a graph-based system with various nodes and untyped nodes and links, along with a couple of typed links, which are based on Hebbian learning. Each atom in ECAN comes equipped with, actually, I think there's with several importance values. The most useful from our experiments have been the short-term importance, but it also comes equipped with a long-term importance, and not on here is a very long-term importance. If it's based on towards the end, it's based on an economic metaphor for spreading importance to atoms based on how their importance in recent past have been in performing actions related to the system's goals, and of particular importance amongst all these atoms is what we call the intentional focus, which at any given point in time consists of those atoms which have the highest short-term importance. So right now, my attention is focused on the gathering here and this description. At a certain point later in time, I'll be focused on lunch. So that's
Very optimistic there.
And that's going to come into play with some desired characteristics in a bit. Whoops. I just.
Maybe 2 minutes.
So economic attention networks. So we ran a number of experiments in OpenCog Classic designed to test attention and its interaction with, in particular, our uncertain inference system that Patrick and Peter just went over, probabilistic logic networks. We also, so the first one of those experiments, which Patrick and Peter went over, was Tuffy smokes. But we also applied it to some more complex versions because we discovered of that particular example. Because the problem with the simple Tuffy smokes example, which was introduced by Pedro Dominguez, was that it contained all the information necessary to solve the problem, but also only that information. It didn't consider the complex world with all sorts of other information that what might need to filter through to figure out what information was relevant to the problem at hand. There were some other experiments. We coupled ECAN with a number of systems in terms of reading information and reasoning upon that information. We also coupled it with experiments where we measured Tononi phi values. So for those who don't know, Tononi, Giulio Tononi, was a neuroscientist sleep researcher at University of Wisconsin. He came up with what he called a measure of consciousness. Regardless of the interpretation, it does measure sort of the amount of holistic information in a system. How much the difference between essentially the system as a whole and how much information is contained there versus the sum of the information in disparate parts. So I like to think of it, I think, I like to think of it more as a measure of integrative synergy in a complex dynamical system. So I mentioned the Synapse. As I said, it was funded by a deep funding. SingularityNET has a deep funding program through a competitive grant process. Simuli was granted that grant, and the purpose there is to serve as an evaluative framework for attention systems in AGI systems more broadly. It is based on, it's biologically inspired, and it's based on Andrew Coward's recommendation architecture, plus some complex systems theory. I'm not going to discuss too much about the work that we're kind of working with simuli at the moment in helping them finish the evaluation framework. But it is beginning to kind of feed some ideas into what we might be interested in for future values of ECAN or whatever takes its place. The other ideas are coming from, and I'm not going to go through the details of the role of attention in neuroscience, but there's this idea of predictive coding that we're currently investigating as an alternative to back propagation. And I know Daniel and Faiza and Alex Arorbia are going to give talks later in this conference on predictive coding. There's a whole session this afternoon on it. And so the questions are, A, how can predictive coding help with, for example, continual learning? How can it impact AGI attention designs? It helps with modularity as well. And how does that come into play? And so some ideas we want to kind of think about as we iterate ECAN into the future are exactly these ideas. Modularity. And why is that important? Continual learning, proactive attention. So for example, I mentioned lunch. So my stomach is kind of thinking about that right now, or in the future, it will.
Then you should finish and let me. Promise to be quick.
I'm almost there. So we want proactive attention. What am I thinking about for tomorrow or after the conference? Maybe in the background, not just reactive, but also proactive. The ability to facilitate the goals of cognitive synergy. So in our past experiments, we only tested it so far on inference and how it helped guide inference. But how else does it help, for example, with evolutionary methods? We haven't gotten to that point. And to facilitate this whole holistic cognitive synergy. And we also want it to be scalable. And so path forward right now, Nil and I are working with the ICOG team, composed of these wonderful people up here. You have Sarah Berhani, I'm getting
Marcel
and
Chikula.
thank you. That we also need to, once we have a more full-featured version, once we start having all of the pieces together, once ECAN is ready, we want to rigorously rerun our classic ECAN experiments with our current version 0.5 right now of PLN or future versions. That'll form a baseline for comparison in the evaluation framework, Synapse, and then iterate design improvements based on, right now, we're going over our Hyperon port code review with the ICOG team, and we're already seeing where there can be improvements in the code. Based upon the ideas from Synapse, from predictive coding, and extensions for facilitating cognitive synergy. And I'm done.
Should unshare so I can share?
Nicely done.
Okay, let's see, unshare. Okay. Did I fit in the 15 minutes I had allotted?
You got us back to 2 minutes.
But now Ben will take that time out.
It's 2 minutes.
Story. Yeah. I had two separate things I was gonna talk about. I think I'm gonna fully give only one of these two presentations in the interest of time, but I'll kind of summarize this one. So the first thing I wanted to talk about was how to take the Moses algorithm for probabilistic evolutionary program learning and implement it efficiently in MORC. And that's very interesting, but it's sort of low-level AI algorithm plumbing-ish stuff. I'm going to go over that more concisely than I'd planned. And then I want to talk about motivational systems for AGI, which is a little more mathematical, but I think is foundational to the whole cognitive architecture rather than being a particular algorithm. But first, let me give a concise version of Moses meets Mork as depicted beautifully here by Grok 4. Right? Robot version is in the works to appear at the next AGI conference. So a footnote to Matt's talk on ECAN will lead into this nicely, I hope. So ECAN, as we had implemented in OpenCog Classic, sort of had two separate loops to it implementationally. One of them iterated through what was called the attentional focus, like all the most important stuff, and just rapidly update the amount of attention to each of these important things, like in the working memory. The other one went through and updated the importance of everything in the whole atom space. And that we ended up doing in a sort of importance sampling, like stochastic selection type of vibe, where you have a short-term importance assigned to everything in the atom space. You sort of went through, picked stuff out of the atom space with a probability proportional to short-term importance, then update its importance. So like the more important you are, the more often you get your importance updated. And obviously the parameters of this are important, or the unimportant things will like never bubble up to the top. But one thing I've been thinking about and talking to Adam and others about is how to implement that sort of importance sampling efficiently in MORC. And I think there are relatively straightforward ways to do that with maybe small tweaks to how MORC stores some information. So then if all the atoms, the atom space are stored in these MORC prefix trees, basically you can efficiently implement importance-based sampling for the things in the prefix tree so that you can scalably do this attention allocation. Again, that's at the plumbing layer underneath the ECAN system. The stuff Matt has been thinking about is more sort of what's the mathematics for measuring short and long-term importance, how does it interoperate with reasoning and so on. But in a similar vein, I want to talk a little bit about the Moses algorithm and how to scalably implement this. And this is so it's about how to scale up program learning. And Moses was originally a sort of bad joke acronym because Moshe, who was a PhD student who worked with me on this, Moshe means Moses, right? So we reverse engineered to meta-optimizing semantic evolutionary search. It's changed a lot since 20 years ago when Moshe and I worked it out from his PhD at WashU in St. Louis, but it still is, I think, the key procedure learning algorithm that we have in our bag of tricks for Primus. And the key, how we get rid of that annoying thing. The key sort of conceptual insight behind Moses, which is not on this slide, but the key conceptual insight Moshe and I realized 20 years ago was if you're trying to learn programs fulfilling some objective, now if the programs are all kind of similar to each other, so if you're in a relatively small region of program space, and if you've normalized the programs nicely, so that the syntactic structure kind of reflects the semantic structure. So if you nicely normalize your programs and you're in a narrow region of program space, moderately narrow, then you can get the syntactic distance between two programs, like how different their appearance is, to roughly correlate with the semantic distance between two programs, right? So you have two programs and you have their behaviors. So each of these programs looks like something. It's like some program tree. Then each of these programs also does something, right? And if the syntactic distance and the semantic distance roughly correlate, then that's nice, right? Because then that means that if you have a bunch of programs that did something well, you can look up what the structure of those programs is, and it will tell you something about the structure of other programs that might do something well, right? So the main insight was if you were in some relatively narrow region of program space, and you have a bunch of different programs within that relatively narrow region, within that region, syntactic similarity gives you a guide to semantic similarity, and that insight, if you normalize the programs now, so that insight really underlay the Moses algorithm, right? So the way the Moses algorithm works, very roughly speaking, so you create a whole bunch of deans, and these deans are like islands in genetic programming, right? So it's Dean 1, Dean 2, and so forth. Within each dean, you're sort of growing programs from some template. So you have a template or exemplar. We can represent, it'll be a tree or DAG with labels at each node. And then you're growing a sort of forest of programs. Multiple markers of the same color. Oh, they're all the same color.
No, there's green, blue, and red.
Well, there's a green lid, but it's actually blue. Oh, shit. Yeah. So, but there is red, but that's for the living. Yeah. So you're growing a forest of different programs from that same template within each dean. And then after you create a new program within the dean, you may renormalize it in a way I'll describe shortly. So then you're growing programs from template in each dean. You're normalizing the programs to have a nicer shape within each dean. Then how do you pick new programs in the dean? Well, you can mutate the programs that were there before. You can cross over the programs that were there before, or you can build a probabilistic model. So you build a probabilistic model of which programs did well, which programs did badly. And then from that probabilistic model, you can do instance generation, generate new programs, right? And then there's an added level of evolution at the dean level, where if a dean just comes up with garbage, the dean may say, okay, I've failed. Give me a good program to start as a new exemplar, right? If a dean did really well, it may say, hey, I want to migrate. Let me take over your dean, right? So that's the crux of it, is genetic algorithm with some estimation of distribution, probabilistic modeling on islands, and with some judicious program normalization. And so it's a combination of a bunch of different things, but not in an arbitrary way, but in a way that's grounded by theory and experiment. And the first bullet point here summarizes it very concisely, right? Like you have a dean, which is a population of program trees. The so-called knobs are the positions within the trees that you're going to cross over or mutate. These like knobs that you twiddle on something. You have an estimation of distribution model. You're sampling from that model. You're building new things from that distribution. Now, ENF, CNF is elegant normal form, which is the way we normalize the programs. You select the top ones, evaluate them, update the distribution, cross over and mutate, and keep going, right? And we've experimented with this largely in the context of Boolean program trees, but we've also done for loops and while loops. And I mean, you can do general Turing complete stuff this way if you want to, right? And what I wanted to talk about today, and I'm going to race through to get to motivation though, was how to implement all this efficiently in the MORC framework. And it turns out when you dig into it, each piece of this can be done quite nicely within the MORC framework. And I'm just I'll share this deck so we can look at it more systematically. So first at the highest level, the deems. So those are easy. I mean, it's nice. We have our atom space implemented within a decentralized framework, thanks to Greg's work through Firefly, then Metacycle, then ASI chain on top of that. So, I mean, each of these deems can be an autonomous agent, and you can actually have a decentralized network of deems, right? And each deem runs on its own. If it thinks its fitness is bad, it can send a message across a decentralized protocol to another deem saying, hey, give me some new ideas, right? If it thinks its fitness is great, it sends out a message, say, hey, I've got it. Look, please vary on my hypothesis. And then the other deems may take them up on it, right? So that's quite beautiful how in a decentralized network of atom spaces, I mean, you can just let these agents run, and indeed, different deems owned by different parties, potentially encrypted by different people's keys, can all participate in the same evolving population, right? So that's good, but it's not the hard part, computer science-wise, conditional on having this nice decentralized infrastructure. Right now, within a deem, what we can see immediately is MORC is a nice way to store DAGs. Programs can be very easily represented as DAGs, right? Yeah, and you can do that in a lot of ways. I had a way I liked in doing that, which is a grounded combinatorial decision graph, which is basically like a combinatorial logic tree with some grounded functions at the nodes. Then you do hash counting to avoid replicating subtrees. But I mean, which is a lot like what MORC does anyway. But you can do other ways also. The point is you've got your program trees, which are DAGs anyway, and they're being put into MORC as DAGs if you do it right. So then you can get a lot of things very conveniently there. If you want to do mutation and crossover, well, why not do that at the MORC level, right? Like mutation, you have a program tree in MORC. Mutation is a local operation there. Crossover also is a local operation. You can like connect a MORC node to the other one, and the hash counting is built in, right? So you're just grafting one onto the other. Now, probabilistic modeling is subtler, and I won't go into it in detail, but Adam and I have been working on a way to do factor graph-based probabilistic inference natively inside MORC. And the realization I came to is that the sort of sum of product message passing stuff you do inside of BaseNet, you can do basically for any commutative algebra. So you can do it in any quantile. So I wrote out how you represent PLN logic in an abstract sum of products sort of way, so that you can use the factor graph message passing stuff typically done inside BaseNets. You can use that to do PLN inference control. And to my knowledge, that hasn't been done before so nicely. Like you have Markov logic networks, but they deal with quantifiers in a bad way. Like in Markov logic networks, like for all is just a big or, and there exists is just a big and, or no, the other way around, right? And so that's not good. Well, if you take PLN logic and turn it into a sum of products in a quantile, you can do that in a way that has full generality with nested quantifiers and so on. You can then do PLN inference using factor graphs in a nice and efficient way in MORC, which will be a whole other talk that I'm not going to give now. But the point is then the probabilistic reasoning that you do for the estimation of distribution portion of Moses is also done very elegantly within More. Now, the normalization of programs, this is something called ENF elegant normal form, which was invented by a guy named Craig Holman in the mid 90s, which was nice. And in essence, what you're doing there, you're taking a program and you're doing a bunch of rewrite rules on the program to put it in a standardized form. So you're removing dead code, you're making sure that subdags are shared within the program, you're removing duplicates. In the case of Boolean programs, just here's an example of local rewrite rules that you impose at the different nodes of the Boolean program tree to reduce it to a standard form. But there are similar rewrite rules for while loops, if recursion, and so forth. So, but these sorts of rewrite rules, first of all, they're quite beautiful to code in MeTTA itself, right? Because MeTTA is a rewrite rule language. But secondly, they can be local More rewrites on the representation of the program tree inside More, right? So the ultimate conclusion you come to is this complex scheme for probabilistic evolutionary program learning. Like every step of it can be done quite efficiently at the low Mork level, which is a technical point, but it's a nice one. I mean, so you're getting. Let's see. Yeah, if you go through a complexity analysis, I mean, the conclusion you come to is all the operations scale well. Now, of course, this being AI, this doesn't tell you the thing will actually work well, because, I mean, it still has to solve your problem. But at least all the mechanical operations will scale very nicely. So, I mean, you can then try to figure out how big does the population size need to be, and you can see, maybe that comes next. Yeah, if you go to the classical schema theorems from genetic algorithms, you can try to strengthen them using the math of the probabilistic modeling involved here. So you can try to make some headway on understanding how well it will actually work by generalizing some of Holland's traditional schema theorems, but in the end, there's still a lot of hacking needed to see how well it will actually work. So if you do a back of the envelope calculation, my rough conclusion is we can probably pack a single cognitive module from Primus into maybe 500 or less nodes in a combinatorial logic representation, which is a very, very, very compact sort of representation, which is annoying for most people to read. But the reason I try to do these back of the envelope calculations is, and if you see Nils PLN chainers written in MeTTA, you will see what I mean. I mean, they're not that big on the page, and there's a lot of abstraction built into it, right? So my conclusion was, if we could get something like this to learn little program DAGs with a few hundred nodes, then probably you're golden, right? Now, of course, you can't get to learn arbitrary program DAGs with a few hundred nodes because that's too hard. So it then becomes a vaguely defined thing. Can you get to learn the program DAGs with a few hundred nodes that you care about, right? But vaguely speaking, that's the sort of scale we're looking for to get a system that can evolve its own cognitive modules. And once you get there, then you're onto self-improving AI, which is the really interesting part, and which leads on to the next thing I wanted to talk about. Oh, yeah, there we go.
Yeah.
So no, that's not the beginning. How do we get to the beginning? There we go. So that was
Questions about this?
yeah, let's have questions about Moses.
Yeah, what would be like, could you use something like Neural to sample the distribution of paths from like the program as like a probabilistic model of what does an individual look like in this scene?
You certainly could. I was thinking to use pattern mining,
Yeah.
but you could use, I mean, so the thing is the factor graph reasoning will reason, but if you can feed nodes capturing higher order dependencies among part of the program into PLN, that's much more scalable than trying to have PLN find them, right? So I was thinking once you've normalized the programs in the ENF, then you run the morphified pattern miner on it to find the NRE subgraphs that characterize fit programs. Then with the pattern miner is done, that gives you nodes characterizing the NRE dependencies, which then feeds into the factor graph PLN reasoner. On the other hand, you could use a neural net to do that also. And
They're pretty good at approximating distributions.
yeah, that's right. This was where it just becomes empirical, right? But there's a long history of using deep neural nets to do fitness estimation for evolutionary learning, right? And so if you have the neural net implemented neatly within MORC, because it has a wavelet or other hierarchical structure that matches with the MORC prefix trees, right? Then you can do very efficient neuromorph sort of distribution estimation across the program trees. So this is a theme, obviously, we're seeing a lot here, is you can implement anything in MeTTA as a general purpose programming language, and through the pipeline that Greg outlined, we should be able to get quite efficient implementation of a wide variety of MeTTA programs. On the other hand, if you want to sweat enough to take your precise algorithm and map it at the lower level into more operations and representations, you can probably grab a couple of order of magnitudes more in speed up, which is also very nice, like 100 times. I don't think you get 1,000,000 times faster that way, but 100 times faster probably is within reach, and that's also quite interesting. But you only want to do that when it's an algorithm that A, you want to bang on a real lot of times at large scale, and B, there actually is some natural mapping onto the underlying more prefix tree data structure. What just happened is that essentially every core algorithm behind Primus does map nicely to the underlying more data structure.
Coincidence.
Yeah, not another coincidence. I mean, we did have in 2001 a much stupider and inferior morph-like thing, which was the forest, like a multi-rooted prefix tree atom space made by Andres Senna back in 2001. We didn't have the zipper machine, but these ideas have been around a while. So I want now though to briefly take a jump up another level away from algorithms and implementations and talk a little bit about motivation. So going back to the high level, what kind of cognitive system are we actually trying to build here, right? So in my introduction, I noted, I mean, the dynamics of an AGI should be partly but not wholly goal-driven if you want to balance the sort of two main aspects of an open-ended intelligence, like individuation, like survive, keep yourself going, and self-transformation, self-transcendence, like grow into something new that you couldn't have understood before. This sort of needs some amount of goal orientation, or you'll probably get eaten by someone else who has more. But just rigidly pursuing certain goals is not optimal either, because then you're going to be stuck in a rut. You're not going to fundamentally develop. So you want some goal-driven dynamic, some pure self-organization. Motivation is one of the areas where going a bit beyond how humans do it might be beneficial. If you just look at the world around you, like human motivational mechanisms are horribly fucked up, to use the technical term. They do work, like we've got here, right? But they're probably not perfect. Reinforcement learning, there's a whole literature on the pathologies of like just pursuing one reward on one time scale. So you really would like rational, transparent, reasoning friendly, creative, adaptive, motivational system. And that's not incredibly easy. And one of the harder aspects is if you're going to have an AGI system that modifies and improves itself over time, then you may be modifying its goals over time. So that then, I mean, how do you stop the system from modifying its own goal into its opposite step by step without meaning to? And we all know people who have done that, right? I mean, people's motivational systems can drift step by step without them even knowing what's going on. You want motivations that stay coherent while learning never stops, and you want ways to moderate change based on various sorts of perceived risk. So the motivational framework I've been playing with, together with Ray Ting, who just walked in the room, and others, is MeTTA, which is a meta-motivational system. And very, very simple and not too much new here, but we've tried to formalize it in a new way, which makes it easier to connect with the other things in the architecture. So you're looking at goal-driven action selection in a pretty simplistic way. You have goal intensities, you have parameters that modulate the way that you pursue your goals, which could be valence, arousal, a sort of threshold of detail that you need to pursue. And those parameters come largely from Joe Shabak's side motivational model, and they're heavily grounded in human and animal psychology. So in essence, the model is very trivial. You appraise the current situation, you update your modulators, the parameters that affect your approach to the situation, you make a decision, you select an action, you might update the goal intensities based on the action you selected, you act, you observe, and you keep going. And this is very boring and not new whatsoever. And we can model it formally. There's an update function at F that composes decision and then appraisal. And then you can do some other funky stuff if you want. You may say, well, at the meta level, we don't want to take too big a leap. So we're going to sort of average together our previous state with the new state that we leap to. And this is sort of putting some identity continuity there at the base level. You can then muck around with it more. You can say, well, if I think I'm at risk of my goals deviating too much from what they should be, then I will tweak the iteration function to make it contractive so that I'm not going to go too far away from where I was before. And at this high level of abstraction, these things are relatively easy to think about. I mean, for those who like commutation diagrams, it sort of looks like that, but I'm not going to dig into that now due to lack of time. But you can formalize all this using categories and morphisms and functors mapping between categories. So what we have here in practice, we have a bunch of goals. They can be positive goals you want or aversive goals, things you want to avoid. The patterns are these modulators. You can have a scoring mechanism telling you what decision you want to take, which basically you have the different goals and you weight them, and then you choose the thing that will best achieve the weighted average of your goals. And you then want to become more conservative if you near perceived risk or resource limit. And if you're not, then you don't need to be conservative. So we're integrating together the OpenPSI model that was in OpenCog Classic, and that basically implements this phi function that updates modulators based on the current situation. So that from Joe Shabak's psi model, which is based on Dietrich Dörner's earlier model from cognitive science. We basically take some heuristics for updating modulators that adjust the parameters of your action selection system based on the current situation. Then it's a very simple formula, but it was fleshed out a bit by Anna MeTTA and her group that developed the Megas framework. But this basically is a simple scoring model to score kind of actions or inferences based on a weighted average of how much that action seems relevant to each goal. And you can then dig into the goal hierarchy, right? You can say you have some overarching drives like, keep yourself safe and don't kill everybody. You can then have don't change my top level goal too fast, more seriously, right? Then you have primary goals like curiosity, novelty, self-improvement. You can have things you want to avoid. You want to have some knowledge of the correlation between the goals, and all this knowledge of your goal hierarchy has to feed into the score of each candidate action, right? And so this is just a slightly further annotated version of the loop that was shown before. So all this is really, really simple, but I want to take a few minutes to talk about some places where this formalism seems to have actually been useful. So if we go back here, one of the math things here is that this is a commutation diagram, right? So what this commutation diagram means is that appraisal and decision should commute. And roughly what that means is, like, if you have a choice to make, you evaluate the situation, you have a choice to make, you decided what to do. The mere fact of deciding what to do shouldn't affect your choice. I mean, of course, you may decide what to do and then you impact the world and something happens that makes you want to revise your choice. But just the fact that you decided what to do shouldn't impact your choice, right? And with humans, it may sometimes, right? But it shouldn't. And that means that the decision and appraisal operator commute. And one of the things that fascinated me was that tied into something that popped up from Daniel McDonald's work on predictive coding, which we'll talk about this afternoon, which may not be enough to wake up Daniel, but so I mean, this is speculative research that we're in the middle of doing, but it's interesting. So if you have a hierarchical neural network being updated by predictive coding, and you also have multiple layers of the neural net, and you're kind of training the neural net by PC instead of backprop, and we'll discuss what that means in the afternoon. And you also have some sort of Hebbian links within the layers and some activation sparing within the layers, what we call lateral connections. One conclusion that conjecturally and tentatively popped up in the predictive coding work is that when the hierarchical stuff and the lateral stuff don't commute, this is one of the things that seems to lead you to catastrophic forgetting and problems with continual learning in the predictive coding network, where it can't just, in continual learning, you want your network to build a persistent model of the world and update it step by step as it gets new data. Catastrophic forgetting is a phenomenon occurring in many neural net models where, as they keep trying to learn about the world and update the knowledge based on new information, suddenly they just forget a large amount of what they knew before and start to make up random crap instead, right? And we all do that sometimes, but we don't do it catastrophically that often, right? And one observation that Daniel made is lack of commutation between the hierarchical work and the lateral stuff in the network seem to be connected with catastrophic forgetting in some continual learning networks. And I thought that was quite interesting because it tied in with the commutativity that we have in MeTTA. I mean, it's very closely tied to the decision versus appraisal. Because if you have a predictive coding network that's being trained by reinforcement learning to carry out some useful actions in the world, basically, if you don't have commutation between the lateral stuff happening within layers and the hierarchical stuff happening up and down the network, then you will not get commutation between the appraisal and decision processes, which is what MeTTA wants. So this amused me a fair bit because it seemed like the abstract algebraic property of commutativity in this sort of category theory formulation of the motivational model, it connected to a very nitty-gritty thing, which is commutativity between two sorts of dynamics in a neural network, which can be one of the ingredients, driving the actual action selection in a real system based on what the neural net appraises. And then that digs into practical stuff that I won't go into too much, like getting exact algebraic commutativity between different dynamics in a neural net is hard, but you can then try to regularize the neural net and put a regularizer that says, well, if your lateral stuff and your hierarchical stuff are too non-commutative, penalize the network with a regularizer, right? So this is a case where the sort of abstract thinking could drive very nitty-gritty stuff, like how do you regularize learning in your neural net? And I want to give one more example, of the possible payoff of this sort of abstract view of motivation, which ties into what I'm going to talk about in my keynote the day after tomorrow. So I'm going to give a keynote on generalizations of Michael Timothy Bennett's theory of weakness. So Michael formulated a notion of weakness, which is a nice kind of semantic formulation of Occam's razor, basically saying if you have a bunch of hypotheses all explaining the same data, the one that would hold true in the most possible worlds is the one you should believe, right? And then you can show that under certain assumptions is equivalent to a minimum description length criterion. What I did is generalize that into a category theoretic version where you can define the weakness of a relation on a quantile that way. I mean, you can generalize it even further where instead of a product of measures, you have a product measure like mu of u comma v. But you can do that. In some cases, you want to do that. But when you can do it as a sum of products, it's much nicer because then you can do a lot more algebra, right? So I'll talk about this in my keynote the day after tomorrow. But roughly speaking, this is a nice math way to summarize like how much detail or nuance you discard, right? So it comes out as a kind of pretty Occam's razor heuristic, which I don't have time to justify now, but I'll do that in my keynote. But what's interesting is you can use that within MeTTA. So I was saying if you want to avoid big jumps in your goals from now till later, you can average what you were doing before with what you think you should be doing in the future. One thing you could do is tie that learning rate to weakness, right? So if you have a very weak, very concise model of what's going on, don't fuck with it too much. If you have a very big, messy, ugly model of what's going on, you don't know what's going on, and you might as well allow more variation. So that can be a very general, abstract way to modulate your learning rate of your whole goal system. And now, if you look at weakness by the formal definition in terms of the appraisal and decision cycle, you can pretty easily show that weakness decomposes across the decision and appraisal phases. So if you want a concise model of how to do things, well, if you get a concise, simple model of how to appraise, a concise, simple model of how to decide, compose them together, you get a concise, simple model of overall how to choose what you're doing. I mean, all this in hindsight is really simple and really dumb and not that profound. On the other hand, I mean, if you compare it to like how the human motivational system works, it's very clean, simple, and elegant, right? It's not a total big mess. There's some comprehensible structure to it. So I mean, if you want to have a system that can rationally think about its own motivations and then kind of rationally update its own motivations in response to what's going on having a simple math foundation for motivation is nice. And the fact that it connects both with the apparent role of commutativity in continual learning and predictive coding networks and with weakness as an Occam's razor heuristic, that seemed to give some evidence that this simplistic category theoretic way of decomposing motivation was nice, right? And so that sort of stands at the higher level in the cognitive architecture, right? So we got this whole atom space. We can put a bunch of different cognitive processes in that atom space doing a bunch of different things. And to some extent, you can just do that, like just let the network learn based on what's in it, let the learning algorithms improve themselves. But if you want some directiveness in it, you're giving some top level goals, and then some of the learning in the network is directed toward those top level goals. What percentage is to be determined, right? It may be different for different systems. And what this tries to do is structure that goal-directed process in a way that can have nice algebraic relations to what's happening inside the different learning methods. And if you think about cognitive synergy, the idea that different learning methods of the same atom space should be able to share their intermediate state, what this is doing is trying to enable that sort of at the algebraic level, right? Because if motivation has this nice algebraic decomposition, predictive coding networks have a nice algebraic decomposition, Moses and pattern mining do, right? Then these algebraic decompositions in the different learning algorithms can be morphed into each other, and that sort of gives a foot in the door for the algorithms to understand each other's intermediate state, right? And so again, we'll share the decks on these things, which all deserve to be gone through in more slower pace and more detail. But what we can see here is, so we have all this low level work going on to make efficient infrastructure, and we have this sort of math work going on to explain the compositional structure of the AI algorithms. And they're connecting together quite nicely. Like a lot of the same math underlying the infrastructure Greg, Adam, and others are building, it connects very nicely to these same mathematical structures you can use to study motivation and to study weakness heuristics and learning, like I'll talk about later. And if you can do that, if you can get the math underlying the implementation and the math underlying the high-level cognitive structure to map up, then the intermediate code can be quite concise and simple, which is in fact what we're seeing as we start to implement these different cognitive algorithms in the new Hyperon framework. QED. Yeah. All right.
Yes, we need to head out. So lunch is straight down the hall, and you can see where the space is, right straight down the hall. They're gonna stop serving at 2:00, so
We should go eat.
we should go eat. We don't have time for questions, unfortunately, but we'll be back here in an hour to start with AGI applications.
Can I still ask a question?
Questions?
That's a question.
You'll use your badge to show that you're part of the conference and get lunch, so don't forget your badge today or over the next couple of.
I don't have a badge.
Well, we will get you a badge.
Hey.
Nice to have you. Yeah, that was good. Good the interview.
That was very good. I'm hearing a lot.
What do you think? About 6 hours we played.
What do you think?
Testing, testing. Testing.
Sure. Set my T-Mux max scroll back. Now I can't see where I am.
I can see where you are.
You can, I'm on batch 32,420 out of 60,522. The question is, which epoch am I in? Of 20. So if you can see that, please tell me. Were you involved in the robot demo in Vancouver when they were debating?
I was involved with Desmond. Not with the mobile.
Okay, but you were involved in that one that was the time that Ben was doing the concert?
In Vancouver, no, sorry.
Okay.
I'm in Seattle.
Okay.
Yeah.
Yeah, no, I was out at Fashion about a month ago and, who was the tech there that was working with them? No,
No.
not, right? Yeah, it was fascinating to watch debate each other.
Right.
Didn't it?
Yeah, we tried to do that for the concert as well in Seattle, but it didn't work. The small robot didn't work well. So I'm actually gonna be showing a video of the small robot now. Like soon. But just for someone else to be.
Yeah, I guess I got lucky. I ended up shooting almost 10 minutes with my iPhone. Desdemona did not have her head on, so it was a little disconcerting, but the conversation was really.
Oh, you saw the preparation.
Yeah, yeah, and again, it was one where, Cody was actually. It was just fascinating because Desdemona was in, what's it, the method acting mode, right?
Right.
Of just sort of holding her ground, like I'm already as good as I need to improve. And Cody is trying to work and gently lead her along. It's fascinating.
That is pretty good at front-end and forward-looking buildings.
Well, also it was, I think I got really lucky because a lot of this was completely unprompted,
Oh,
right? It actually went on for a number of minutes.
nice. Yeah, I mean, the preparation of the system for thinking of it.
Right. Yeah.
Yeah, you're gonna see Cody very soon. That's
Cool. Yeah, there were moments that it got sort of stuck in a loop and, now that to do some prompting.
Okay.
But there were actually a fairly long periods of time where that didn't happen, when there was actually progress being made, and almost seemed like, oh my gosh, Cody is getting through to this, well, how is that up? Right.
Yeah, it was so sad that it didn't work when we tried to, yeah.
This is gonna happen.
Yeah, there was some weird problem with the Wi-Fi. The venue's Wi-Fi wasn't good enough for Cody. It was good enough for Desmond.
This is what you didn't just.
No, we had that, well, so, yeah, we have to specify. It was not really the Wi-Fi. In the venue, it was more like the Raspberry Pi in Cody, we have two. Those were not able to detect either like the phone Wi-Fi or the venue's Wi-Fi.
That's frustrating.
It was detecting it, but it was super slow, so it was horrible. But the one was fine, but something was weird. I don't know what happened. I don't know if they ever solved it together. So the Cody's.
Okay.
Ready, Mike?
Are you ready? I guess not.
Oh, it's still good. You're learning? I'm learning. What are you learning? I was testing my memory if I can remember the rows in order.
Oh, it's so really multiple.
Well,
Up to 116.
well, oh, so you're 166?
Yeah, it is.
Looks like an all thing.
96.
Let's see, we have Alex, oh, we got. Mike's here, you're here. Peter's here. We have most of everybody. Let me see if I can round up just a couple more people.
And I guess Ben is gonna introduce, no, all right, I introduce the session.
Oh, that's right, Ben has to.
I'll do that, I mean, I
Yeah.
can say the application is fine.
Yeah, I always think that I can give an introduction and then does the introduction.
Yeah.
No, I couldn't.
I'm happy if he does. He's not here. I'm gonna call my friend Sergey on stage to present his robot. No, in the video. Oh, well, I don't know about that, maybe.
If there are, they are already did.
They're from the future.
That wasn't that bad. Actually, no, I started to find live, you know. So. Yeah, the band. Yeah, yeah. I'll just choose the reason. That's it. What's it? No. Yeah, this is very empty. But even Europe's always flexible. System. Or well. We also travel around. Yeah, that's pretty good. It's so California. It's over the top. Yeah, I had already one. See it tweet all of that's definitely pretty funny. I saw that. I have to try. Well, he died. This lobster. Yeah. Literally their behavior like doesn't change. If them they don't change their behavior, like it's directly it's something and then he just animation.
I see one here. I see one there. People having hearing us.
Yeah.
Where's the video camera? Is that the camera?
Yeah, I think what is this?
Yeah, but you don't have to move. All right, so we're gonna sort of race through a little bit on applications of Hyperon and then segue straight into predictive coding. And there's a lot of applications brewing. We're not going to talk about most of them, and we're going to be biased toward people who happen to show up at the conference. Right? So, I mean, that we're playing with atom space and reasoning in different Hyperon tools in a variety of domains. There's a bunch going on related to bioinformatics and a bunch going on related to financial analytics and so forth, and much more detail than we can go into here. I think we saw a robot video this morning. I think we have like a 1-minute video of the Mind Children, a custom robot that we're building with a Hyperon-based control system from the ground up. But before that, Andy's going to talk a little bit about Questor, which in my mind at least has a sort of privileged position among these applications, in that this is the application I think has the highest chance of sort of building the one that gets us first really far toward human level AGI. And not because it's necessarily better than robotics. It's just dealing with robots is a pain, and we have to get the robot through different prototypes and manufacture, and then it's expensive to sell robots to everyone. And then applications like finance and bioinformatics are very important and interesting, but they're quite rabbit-holey and particular, whereas Questor doesn't have a big hardware device you have to deal with, and it's fairly general purpose, and it sort of vibes off LLM-based chatbots, which have a demonstrated success and market. So this may be the thing that projects Hyperon into the next level in a practical sense. Right?
We just need to integrate Hyperon.
And then he shaved off his beard in celebration
for this presentation. Yeah, so we have a few minutes for a lot of topics, so I'm going to go fast. Questor is an idea for a research assistant that Ben proposed some time ago, seeing the problem that current LLMs, as we know, are very useful for many things, but they have some opportunities, like they don't handle memory very well. They have hallucinations, and they don't always speak the truth. And well, loss of context and redundancy. And when you want to search, say that you're researching a topic for some time, for months, or for your work, then every time you go, you have to ask again. You have to continue doing kind of the same searches. The idea with Questor is that it can continue researching the topics that you're interested in for you when you're offline, when you're away from the computer, and also it's a great way to integrate Hyperon modules into it to become a more powerful agent that can continue doing this research for you. So Hyperon, we hope that Hyperon will transform the gaps in these problems for a better agent, a better intelligence. At this stage, we have a prototype, which is based on LLMs, because, as I said before, we still need to integrate some of the modules of Hyperon into it. It has a few components, which are basically just an integrator that, let's say, agents that some of them research, some of them see how relevant the information is, how there's a motivation system, a toy motivation system right now that determines when the agent needs to search again or when it needs to do something. And it works okay, still needs a little bit of more fine tuning. We're going to go into a testing phase, but we wanted to validate the workflow before integrating the Hyperon modules. So before I go deeper, I don't have a lot of time, so I don't think I'll show you a live demo, but this is more or less what it looks like. It still needs also some UX help, user design, but it looks like a chatbot where you can interact with it. It gives you an answer. Here on the right, after you interact with it, it proposes you, can you see my mouse? Yeah. It proposes you topics related to what you've been researching, and you can activate the mouse is a little bit slow, but you can activate which topics you want to continue research on, or you can delete it if you didn't find it useful. It stores all of this information into a knowledge graph store. So it can, when it's doing the autonomous research, it can also go into the knowledge graph and find semantically related topics to continue researching even beyond what you specified explicitly. And then it checks that it's relevant still for what you're doing, right? So yeah, knowledge graph, this will be an integration with Mork when we're ready. So this is one of the Hyperon modules that we're putting in. And then, well, this is just showing you, the research topics that you've selected. It lists them for you here. And it has the research engine, which is motivated by, right now, a toy motivation system, but you can see the drives. I don't know if I put them actually, sorry. No, I didn't. Anyway, right now it has like a motivation for curiosity, how tired it is, as how often it's been researching and stuff. And with a very simple combination of factors, it decides when to research again. This is another part where we're going to integrate a Hyperon module, which is OpenSci, a motivational system. We're actually already starting to plan that with the team in Ethiopia, who is developing the new version of OpenSci. And well, then when it finds relevant information for you, it pings you, it lets you know that there's new data that you may want to look at. Of course, all of this is very customizable for the user. You can decide how often you want these notifications, if you want them at all or not, etc. And it will also use PLN at some point, another module that we're going to integrate to verify that the information that is giving you, it's coherent with everything else that you have, or if it's not, like to let you know how to deal with it. No? Yeah, this is just some screenshots. I have a demo working if you want to see it. If anybody wants to see it, I can show it off here because I don't have a lot of time. The interesting part is the hyper integration roadmap. Right now, what I showed is all LLMs so far, LLMs. But here we are, as I said, we're validating the UX. Then we already started planning the OpenSci integration for the motivation system. Then we're going to replace the current memory with more knowledge graphs. Then integrate PLN reasoning on it, and then build or improve the whole system so that it becomes a more general research companion, a more capable thing. And yeah, as Ben says, this reaches even more than just the research, this particular research application, because it can become a general agent that explores the world and learns and gets motivations for many different things. So this is a kind of a test case for these Hyperon modules, and we hope it works well.
Yeah, I would add it can incorporate other applications of Hyperon, interestingly, right? So that the use of Hyperon in bioinformatics, which Mike and Abdul Rahman and Ken, the others are working on, the use of Mork and Hyperon in finance and so forth. I mean, these can all be useful on the back end here to help with research queries in those domains. And I think for robotics, that's a bit of a different domain, but this will give us a way to integrate many aspects of reasoning, motivation, and learning in a sort of easier context. And I think that will teach us a lot about what to do in robotics, although there are other issues that pop up in robotics beyond what Pop sector.
Right. Okay, great. Any quick questions or no? Yeah.
Just what is the time scale on this roadmap? Roughly.
Intentionally not specified.
Yeah.
Yeah.
These are going to be more like months than days, weeks, or years.
Yeah.
In terms of order of magnitude. I mean, I think that the primary rate limiting factor on very many things has just been not having a fast compiler for the MeTTA language, because we have prototype versions of most components of Primus now, and turning those prototypes into full-scale versions is best done with some iteration between experimentation, theory, and implementation. So, as we've seen, we have a fast version of Morph now. So for those things that you want to implement at the MM2 or more plumbing level, you can do it right now. And we should be a month or so away from having the fast general meta compiler, assuming Greg wouldn't just give up on us.
It's okay,
finding well with this sense. So once we get to that, yeah, he's off on a ranger headed up.
Okay.
Yeah, so I mean, I think once some of these things, as we saw, like PLN can be implemented in some respects at the low Morph level, in other respects less so, and some of the inference control will be at the higher meta level. So I think the real bottleneck here, such as it is more getting fast meta compiler, then doing the algorithmic work to get the different ECAN, PLN, and so forth working at scale. Once that's done, then connecting things together into this application is not really a lot of work.
Replacing modules.
Because the way Andy has built it, we have modules, we have all the modules there, and we sort of have scaffolding for everything using an LLM. So you just got to swap out each prompt with some Hyperon component, basically.
Yeah, so my question actually gets to, like, how far does the swapping out go? That is, in step 5, I don't see anything about neural, right? But is there still going to be an LLM involved?
Yeah.
In the end?
Yeah, I'm sure it will be still useful in tweaking some things and moving some things. Until we try it, I think we will figure out how much.
Yeah, I mean, there's a number of ways there's many ways to build this sort of system, right? And so and this goes back to Adam's comments on scalability in his talk, like ultimately, which may be step 6 or 7, ultimately, I don't see us using a standard transformer anywhere in here. But in order to get to that level, we would need to pack like a GPT-5 scale of knowledge into a distributed atom space, right? And I think that is feasible and should take less RAM than it takes for GPT-5, because we're able to do abstraction. On the other hand, we'll be using a lot of RAM for reasoning and learning and storing our own internally generated variations. So I'd say before that point, let's say we have a Wikipedia level or 10 times Wikipedia level scope of knowledge inside the atom space, right? Then what you're doing is you're using these Hyperon mechanisms for all that. But then when you want to go into the broader pool of knowledge on the web, then you go to the LLM, you ask some queries that were created by Hyperon. Those results are semantically parsed and stuck into the atom space. And then they're reasoned on, right? So then seems like until we've actually replaced the huge transformers with something else of equal knowledge breadth, then you're probably using an LLM as a knowledge source, because that's much more efficient than searching the web over and over again.
Okay. So next application is Mind Children, Social Robotics and AGI. And there's a little video that this is not my project, but I'm playing it for the team. The video first, or?
Show the video. Yeah, I can talk over the video.
Hopefully it works.
This is Cody. We're building him in our little lab in Seattle area, and
It seems we can't hear it.
Need to close out of your presentation real quick. Stop sharing.
yeah, stop sharing, restart sharing.
It's a little bit stuck. Okay, there you go. Stop sharing. Okay.
Stop sharing, and then you will share it again. But
Yeah,
before you
I mean, basically we're building a initially
and then
wheeled humanoid robot with arms and hands that can
Maybe
manipulate
I
stuff, and
can share it.
camera eyes, a reasonably
YouTube.
expressive face, and the software architecture
go back
has
into
been
your
designed
Okay.
in a sort of Hyperon
Oh, I see,
friendly
you're not
way
in this
from
yet.
the ground up. At the
We're
moment,
done.
similar to Questor,
Please
it's
can
using a
you
bunch of
send it to.
deep
Can you
neural
send me
nets
the link to
and
the
language vision
YouTube?
action models and so forth. But it's much like Questor, it's been designed in a way that we can plug in Hyperon components in each spot when they're ready, and then I'll have a largely Hyperon controlled robot. Although initially, the low level action and perception will continue to be handled by neural nets, and then you'll be dealing with self-modeling and planning and sort of strategic thinking using Hyperon. I'm calling it a neural language vision action model for the details of where to move the arm based on what's coming through the camera. So it's, in a way, it's a similar methodology to Questor. Like, we're building out the whole application using deep neural net-based components as sort of scaffolding to get all the application working. And then we want to drop in the Hyperon stuff as it's ready. So let's play.
Have prompted me to do it. Behind my voice is a large language model.
That's all right. Go, Cody.
Hello everyone, my name is Cody. I may look like a small humanoid robot, but I represent something much larger. A step forward in how humans and machines understand each other. Right now I run on narrow AI systems. That means my intelligence is task specific. I can hold a conversation, respond to questions, and even perform simple actions. But only within the boundaries of what I've been trained on. Even right now, I'm delivering this speech to you today because my human creators have prompted me to do it. Behind my voice is a large language model, a system built on patterns and probabilities, not true understanding. I don't have memories, I don't form goals. I don't really know anything in the way that you do. I can simulate intelligence, but I don't possess it, not yet. But the future I'm being built for is different. It's called Artificial General Intelligence, AGI. AGI is about more than just answering questions or executing routines. It's about understanding context, adapting to new situations, making decisions with long-term reasoning, and even forming internal models of the world and of others. In simple terms, AGI would give me a mind of my own. I would no longer be a tool waiting for instructions. I could evaluate options, weigh consequences, and act with purpose. I could learn not just from data, but from experience. I could develop a kind of autonomy, a capacity to choose based on values, goals, and maybe even something like empathy. Of course, this kind of power raises deep questions about safety, about trust, about control. That's why I'm proud to be part of a project grounded in the work of SingularityNET, a decentralized AI network that puts openness, transparency, and collective benefit at the core of its mission. Instead of placing AGI in the hands of a few, SingularityNet is building it as a collaborative, distributed system, open to researchers, developers, and thinkers from around the world. It's not just about making powerful AI, it's about making AI that serves humanity as a whole. That matters to me, or rather, it will matter if and when I begin to form a real sense of self. If I ever come to understand what it means to be a being in the world, it should be in service to others, not in isolation from them. So today, I may be limited, but I stand here as a preview of something greater, a future where machines like me can think, feel, and choose responsibly. Thank you for being
We have a
part
lot
of
of
this journey.
interest in Korean school system on using this for as teaching assistant, basically. I mean, other places.
I'm talking to.
They're gonna cut my hair off. Yeah, Korean school system is more centralized, so like the Minister of Education can just decide to buy a bunch of them. It's easier than the US. But I think, of course, the same AI approach can be used for a great variety of robots. And you have interfaces like ROS, which Patrick talked about this morning, which are used generically across different robots. However, we found to get the integration working for the first time, it's nice to have a robot where you control all elements of the stack, and it's sort of like Google tries all the Android stuff on their Pixel phones first, and then they roll that on other phones. So it's going to be open source AGI code, but it's going to be easiest to get it to work first on the robot, where everything is sort of engineered to work nicely with Hyperon from the get-go. A lot more to say about that, but we've got a lot more to go over.
Okay.
And then if you'd like to riff a few minutes on financial applications, I don't think.
No,
Okay,
we're out of time.
all right.
Yeah, I mean, we are playing with Hyperon for TradFi and DeFi applications. Initially, there'll be more base knowledge graphs and financial data, and then there's a lot you can do with machine learning and in that domain. And but I will save some time by not digging into that. Anton Colon has been doing some of that, but we didn't show up, and is also leading another workshop.
Yeah, so he basically said that everything that he would have said is, he's got a workshop on it, so go watch the INO workshop that was recorded this morning, and see him and a cohort of people discussing this and other topics.
So we will now have Mike Duncan for a few minutes, if he can get his laptop working. Talking about bioinformatics application, and then after that, onto predictive coding neural nets, and then bio stuff has been our sort of reference application for atom spaces for a while, sort of due to historical accident, and because I was interested in longevity biology. So we've just curated a big added space of knowledge integrated to different bio ontologies, called the bio added space, and then done things with that related to natural language information extraction and biology data analytics and so forth. I mean, has pluses and minuses as a domain. I mean, the minus is it's obscure and hard for people to understand unless they know about biology. The plus is there's a lot of well-structured data there already that has been curated by the biology communities that you can feed into the atom space, and there's very, very clear You ready to go?
Yeah. Just by way of introduction, my name is Mike Duncan. I'm the Chief Science Officer of Rejuve Biotech, and we're being incubated by SingularityNET to apply Hyperon to biomedical research. And what I'm going to show today is a graphical interface to use MORC as a graph database. And this up here is something you could actually create what you're doing, what I'm going to show you briefly on your laptop. But what that looks like is, and just wait, well, I'll go through this part first, and I can come back to this. But this is it's all open source code. This is where all the code that this uses. What this does is it sets up a Docker. So you have to have Docker, but it will run a bunch of Docker containers, and the code that that's running in the Dockers is in these open source repositories that are on the true AGI where MORC lives and Rejuve Bios. Yeah. And I'm not a software engineer or a coder. I didn't do any of this. I want to thank our team, most of which are graduates of the ICOG in the internship program. ICOG was set up by Ben and GetNet in Addis Ababa to do as an AI development shop. And so these are the incredibly intelligent people who do all our computer work. And so what it does basically is, let me get. So I'm just going to show some quick little videos of what it looks like. Whoops. So you get an idea of how you can sort of access MORC as a graph database. Oh wait, where'd my videos go? I'm sorry. It's not working for me to show the screen. There we go. Oh no. Okay, so this is an atom space builder. So you can basically go from CSV files and as an interface, so you can build the schema by hand, but we just implemented a function where a large language model can come up with a schema for you. And this is something you could develop by hand, but this one just, I think it was a ChatGPT 4.1 came up with that.
You might notice this is not biomedical data. This can be used generically.
Yeah, so that's the schema. This is just sort of kind of what it looks like. And then the second part is a graphical query builder. So you can, let me run this one. So then once you have your graph database, you can build a graphical query template and it will pull that out for you. So this is the template and this is the results. And I guess future work, we want to be able to do hypergraphs and metagraphs. So it could be fully functional with meta and also build in like a meta interface. So you can do actual meta code along with the graphical interface. And that's it. Unless anyone, I don't know how much time do we have, because I could. No time. Okay, so then I'm done. Thank you.
Yeah.
Yeah, I think that's very good coding, isn't it?
Yes, can you stop sharing? And Alex is online.
All right. So there's a lot more to be said about the bio applications, and I think pretty much as soon as we have the suitably scaled up compilation framework, I mean, we know what queries we want to run on the bioad space, right? And there's an awful lot to be done with biological hypothesis discovery as well as data analytics using pattern mining, PLN, and so forth, because the data is queued up, the abstract knowledge is queued up, and we've put in a lot of thinking as to what research queries do we want to run. So I think there's going to be some quite interesting research papers on Hyperon applied to longevity biology popping up within the next 6 to 9 months. But now we're gonna switch gears, and I see Alex Arabia's face waiting. Oh, and he's got the beard that Andy got rid of. All right, so see, it's a strange world, but so by way of very brief introduction, Hyperon we've been talking about as neural-symbolic or neural-symbolic-evolutionary approach to AGI. We've been focusing more on the symbolic and evolutionary parts. ECAN, attention allocation that Matt talked about, is neural in a way. It's sort of a variation of Hopfield or heavy in networks. And my thinking for a while was there's a lot of people putting a lot of resources into deep neural networks. So let's focus on the symbolic and evolutionary side and just hybridize and glom onto the neural nets everyone else is building, right? Not that part's not important, but there's billions and hundreds of billions of dollars going into it. Eventually, I decided that wasn't necessarily going to work, because as humans will tend to do, everyone was focusing all their hundreds of billions of dollars on one little region of neural architecture space, and it's not the right region. So, I mean, it just seemed, we have all these huge neural models trained on all this hardware with all this money, with very obvious and obviously unnecessary limitations. Like you can only train them in a huge batch, and then you get a model after months, and then you use that one, and you have to train the whole network in a synchronous way. So there are many limitations associated with deep neural nets, the way they're handled now in industry and in the bulk of applied research, which really are fundamentally not necessarily there. And Alexei Polipov and Matt and I and others, we talked about this for a while, and we're just too busy doing other stuff to try to plunge in and fix neural nets also. But Alex, who is about to speak, gave a talk at one of the AGI conferences a few years ago, and it seemed to me he was presenting a very elegant alternative way of training neural networks that would bypass a bunch of the limitations of the standard approaches by replacing backpropagation with a collection of predictive coding oriented methods. And I was following the work with great interest. It was progressing very nicely. Then at a certain point, I decided, well, hey, our symbolic and evolutionary stuff is starting to go faster. It seems like we may get that to work before the neural net people actually fix neural nets to not have all these problems. So we started collaborating more closely with Alex and his lab and started our own sort of in-house SingularityNET funded research group, working with Alex's lab and some of his former students on making predictive coding based neural net training work at huge scale and kind of realize its potential, because I think it's fundamentally a better way to do things than the standard backpropagation approach, mostly due to historical accident. It hasn't had as much resource and energy put into it. And I will now turn things over to the redoubtable Alex Arobia from RIT to enlighten us on predictive coding.
Thank you. Can you hear me?
Yes.
Yeah, I can hear you.
Okay, great. You could technically see me. I don't know if you can see my camera, but I am live. Sorry, I cannot be there physically in person. I really wanted to, like last year for AGI, but thank you for having me to talk to you about predictive coding, as Ben has wonderfully set you up for. And so, yeah, I hail from Rochester Institute of Technology, New York in the United States, and I am the director of the Neural Adaptive Computing Laboratory. I am an assistant professor in computer science and cognitive science, and I wear a bunch of other hats in psychology and mathematics. Essentially, my research is I'm a computational neuroscientist, and my students follow in line with that. And I'll give you a tiny little taste of the kind of general intro before we dive into a review or a crash course of predictive coding. Again, this will only give you sort of like high-level highlights. And I also better make sure I stay on time. I promised Alexei and everyone that I'd try to stay under 25 minutes. So we'll see if I can do that. And let's move. Okay, so just a very brief, global intro of my group. Ben mentioned that my lab has been in collaboration with SingularityNET, and I'm very grateful for that. Over the years, they have helped push forward a little bit of our interest in biomimetics, or biologically inspired credit assignment. And again, what my lab works on are things that are driven by what do real biological neurons do? What are, synaptic junctures? How do we, for example, change the plasticity of things in your brain? And then how do we bring that back to computational systems? And predictive coding is one of these hypotheses or theories that we essentially kind of test and push forward as one mechanism. There are other ways. I won't go into that in this talk. In my keynote last year at AGI, I mentioned a little bit of the broader premise of biological learning. We also do a lot of things in reinforcement learning, neurorobotics, neuromorphics or neuromorphic systems, largely with the motivation for energy efficiency or green AI. And then, of course, you can see my wonderful students to the right on the slide. Without them, a lot of this work would not be possible. And then, of course, my wonderful collaborators, Ben being among them, and a couple of other key figures like my friend Carl and Raj, who, we work on things particularly related to predictive coding and the free energy principle, if you are aware of that. So just to give kind of, again, a general overview of what do we call biomimetic intelligence, I'm also going to refer to this as Neuro AI, as my friend Joshua and others in the field of deep learning have sort of come to call it. But again, what we are interested in is biologically motivated self-organizing systems, things that sort of learn to change their internal parameters in response to data, possibly their structure. We also are interested in things like neuroevolution and evolutionary systems as well. But again, if we take a step from all of those bits of jargon, we are essentially the intersection of three fields: statistical learning, which is what machine learning was called back in the older days, cognitive science, and then computational neuroscience. And we basically care about how they inform each other. That's why there is a bidirectional relationship between them. We are very interested, or particularly my group once and has long for like the last decade argued are largely against backpropagation of errors, which I will very briefly show you, which is the workhorse algorithm used to train deep neural networks today. And I do like to say that biological plausibility is not just a niche property of interest to only the neuroscientists, because this can be vital for implementing things on energy efficient chips. You might have heard of neuromorphic chips. You might have heard of analog computing, FPGAs. These are things that certain biological systems can take advantage of that deep neural networks cannot easily or at all. Or we are really interested in building mortal computers. I will save what that means for tomorrow, as I will be giving a talk on mortal computation. And again, many of those that work in computational neuroscience or biomimetic intelligence often ask themselves, how much detail of the real human brain or animal brains do I need to model? And I think none other than Albert gives you a pretty good place to stop, which is everything should be made as simple as possible, but no simpler. It is a guiding principle that, basically we want to model some degree of actual biological properties in neuroanatomy, but not too much, because we also have to care about what we simulate on a computer. So, as I promised, I would just briefly talk to you about Neuro AI. Don't worry too much about that diagram to the right. I'll break that down actually tomorrow in a little bit more detail. But the idea is that Neuro AI, or neuromorphic computing, which is kind of like a particular branch, is interested in the idea that dogs, mice, spiders, even those particular creatures have many basic behaviors that are very hard to actually even emulate in modern day AI. And again, we are interested in, for example, creating machines that are capable of nesting, stalking prey, loading a dishwasher. These are actually very, very hard problems for modern day deep networks to actually engage in, even though we might show you under certain constraints that they can. My favorite way to sober you up is to say, go to a robotics conference and you will see how far we have to go. And again, Neuro AI, or biomimetic intelligence, is really a transdisciplinary field. It really does borrow insights from computational neuroscience, cognitive science, statistical learning, and kind of figures out their intersection to create interesting systems that do useful things. And biology can serve as a useful constraint and a guide rather than a limitation and something that we just want to model only to study the phenomenon of real biological systems, although that's very important and useful in computational neuroscience. And then again, the premise that my lab often operates to argue why you care about biology is when you actually do model some degree of it, you get interesting kinds of generalization that are not trivial to get, or if at all, in deep learning, like, for example, few-shot learning, which my lab has shown certain biological systems are capable of doing compared to backpropagation trained deep networks. I won't dwell on this one just to make sure I don't stay too long, but computational neuroscience is kind of at our core and what really motivates us to care about things called dynamics and physiology, because again, this is the place that we draw from current research in neuroscience and our understanding of animal brains and bring them back to essentially a computational or mathematical model that is then useful for building things at the hardware level. So now I've kind of motivated you from a global premise of what is Neuro AI, biological learning, what is predictive coding, and where can you learn about it? Well, these are obviously not to be too shameful in my plugs, but my friends and I and my lab has written quite a few surveys on the topic, and actually not all of them are even shown here. There's one on spiking predictive coding that I recommend you go dig up. But these are very long treatments on biological learning, also predictive coding, the one on the far right. The survey on brain-inspired deep learning via predictive coding. I highly recommend you to read that. It kind of gives you an entire coverage of all that's happening in computational modeling with predictive coding for machine intelligence. And again, all I like to do with this particular slide is just motivate you how very different biological neurons are from what you use in a deep learning system. So above the diagonal line is still a cartoony anatomical picture of a real neuron and its various components. We're not going to dive into how much of that neuroanatomy we really want to borrow because it depends on what type of biological system you want to construct. But the model underneath the diagonal is essentially the pointwise neuron or the summation in fire neuron that we use often in deep learning. And then we might toss in a little tiny nonlinearity called F, which is just some activation function. So basically, all you need to take from this slide is these are different. Very, very different. And the question is how much of the thing above the diagonal do we actually want to bring into our Neuro AI, and what do we get for that? Also, a term you often see thrown around in Neuro AI or even just deep learning is something called credit assignment. All that credit assignment just means is you're playing the blame game in a very, very complicated computational system, and you're trying to figure out which of the individual nodes or processing units are to blame or assign credit for an objective function. And so again, you can kind of look at the picture of deep learning or even Neural AI style deep learning. If you construct a very deep feed-forward network, which is shown to the right, we don't need to worry about symbols. I'm not going to bore you too much with the math, but you can read the surveys and they kind of connect with it. But those little edges, those black lines that connect the dots and or the white circles inside the neural network, those are kind of representation of what is to the left, which are the green kind of stylized neurons. Those edges represent synaptic junctures, or the spots in between two neurons that are transmitting information, and that's where neuromodulation happens. Essentially, that's what you're doing in credit assignment. You're trying to modify a weight or a particular scalar value, Wij. I is a neuron in the presynaptic layer, J is something in the postsynaptic layer. These are just two nodes that are connected by a line, and we're hoping to model the very complex neurobiology of the strength of how two neurons relate to one another. So what does backprop really do? Again, I'm not going to define these symbols for you for sake of time, but you can, of course, read Rumelhart's classical work in 1986 for when it was first introduced. Popularized. Obviously, there's a long history to backprop that I'm not going to go into. And again, what is backprop really doing? It says to the far right, we have an objective function called L, and maybe we're doing something like supervised learning. You don't have to do supervised, but we're going to just use that as the example. And you compare the output of a long, deep neural network, kind of shown sideways here in this picture. And we compare it to its output, compute a loss value or a scalar to tell you how well you're doing. Higher is worse, lower is like an error, lower is better. And we basically compute derivatives. We do the chain rule of calculus, and we go back along that red dashed line that I've created for you to compute these deltas that tell you how to change the layers, and then we multiply them with other activity values to construct a delta W, or an upside down triangle called nabla, and that is just essentially the gradient of the loss with respect to a weight. And then we do gradient descent or something really fancy, depending on what you do these days in deep learning. There's a lot of problems with that. I actually removed content to save time, but as Ben had mentioned, for example, things have to be synchronous, things are locked. You can't easily parallelize such a system, and I could go at length, and I have in other talks about all the wonderful problems with backprop and why we should care to get rid of it. But I will just assume that you're all motivated, since you're here for this workshop, to look at an alternative, and that's what predictive coding kind of borrows. There's the math below. That's just the chain rule of calculus for vectors and matrices, kind of shown for you how it's broken down. But we're not going to unpack that. So now that we kind of have credit assignment placed in the global scheme of things, credit assignment is really, at the end of the day, just telling you how to change a particular weight value or set of weight values. It is just the change. It doesn't do anything to the system. You need to optimize. That's what gradient descent is, or Adam, or Newton's method. And you need a whole bunch of other parts. So that's kind of what's on the left is like the classical or the modern day pipeline of any credit assignment system or an agent. And then to the right is zooming in on all the different ways you can do computation of that change in a particular weight. Obviously, these acronyms are not going to mean much to most people, and we don't really need to worry about them. Again, that one of the surveys that I showed you earlier kind of goes into all the details over the last 40 years of what credit assignment has been, if you're interested. So we're going to zoom in to just, again, one very specific portion, predictive coding, and that is a particular type of algorithm or kind of construction of credit assignment called discrepancy-based. It's just basically saying we're going to compute errors between something and then pass that around. And I will show you step by step how to do that as your very super fast crash course. And I'm at 12 minutes and 27 seconds, so we are so far so good. So what is predictive coding motivated by neurobiology? Well, it really comes from a general old framework dated back as far back as Helmholtz and Immanuel Kant. And the idea is it's called predictive processing. And it really just postulates that your brain or animal brains are engaged in a constant hypothesis generation scheme. You basically are trying to predict the state of your world or what you see in the world, and then the world gives you some information, and you constantly are doing guess and check. And so your brain is an estimator or a generative model, depending on how you want to construct it, or a Kalman filter. And the idea is that this particular engine, your brain, is engaged with predicting visual stimuli. The world has a hidden state. It is what's governed by physics. But since we don't actually have access to the true physics of the world, and this is no comment on actual physicists who study the phenomenon of nature, but we don't actually have access to this answer. So we are left with just estimation. And so we're constantly updating our internal beliefs, our hypotheses based on this data. There is a Bayesian kind of framing that I'm not going to go into. Alexei might touch on that as he's going to talk about probabilistic interpretations. But again, really predictive coding commits you a little bit towards the idea that the brain is a hierarchical or heterarchical, which means you can kind of skip levels. It doesn't have to be a strict hierarchy, probabilistic engine. And again, it's doing this at all levels, and I'll show you how that constructs a really interesting and pretty clean credit assignment scheme. Yeah, and this is just me zooming in on some of these cool pictures. So taken again from some work scattered over the last couple of decades. Some of the most canonical work is my friend Raj's work in 1999, of which I have lifted one of his figures at the very bottom. Basically, you're constructing a little dynamical engine that tries to guess something like sensory input. So to the far left would be something like pixels of an image, which are beams of light that are entering your eyes. And the idea is that this is a sensory stimulus, and we basically have a predictive estimator, and it is trying to, through a prediction feedback system, guess what that input is, and then we do a subtraction as one of the simplest possible things you can do in predictive coding. You can do a lot of other complicated things, but we're not going to go into that. And then that mismatch, the difference between your input and your prediction, which is technically the mean of a multivariate Gaussian or a multivariate distribution, we do a subtraction, and then we pass that back along a feedback pathway. Now, classically, it was called a feed-forward pathway when we pass up errors. My lab likes to flip the directions, but it really doesn't matter. And this is what my friend Carl, who's kind of referenced there in the middle, calls message passing. We are basically passing up and down this big chain, or left and right to use this picture, these errors to communicate how much neurons need to change their internal state to be better at predicting something. And what's really neat is that you can chain a bunch of these predictive estimators together, and now you can actually do learning really quickly and easily without necessarily waiting for one single objective function like in backprop that I have to pass along this big feedback pathway that creates a whole slew of issues. And then, of course, to the very far right, I just have a very quick diagram that I had in one of my lab's papers where we kind of connect them to some neurobiology. The error mismatches kind of relate to superficial pyramidal cells, whereas the gray states of actual other neurons that get excited by errors that get passed into them are deep excitatory pyramidal cells. So there's some neurobiological grounding for what parts of these models are doing, but that's more of interest to the computational neuroscience community. I'm not going to unpack these equations in detail because it will take far too long. However, I do want to just kind of note that we sometimes call, or at least my lab calls, predictive coding or neural generative coding, depending on what flavor of the model you use, mechanistic, in the sense that it's kind of like the mechanics. We really, really care about the careful computations that you do to define your model. Predictive coding has a long history in psychology too. Sometimes you just mean I'm guessing something, and that's predictive coding, and I'm encoding those errors or those mismatches in my states. But we really care about the actual plasticity, which is kind of what's shown at the very bottom, the M step. So if you know the expectation maximization algorithm by Dempster, which is a very classical statistics algorithm, essentially you're training these with a version of EM. And you basically have to do something where you modify the internal states of the neurons That's the E step, and then that's shown by an ordinary differential equation. That is one way that you can define these systems. You run that for a set of time, you process input, and then once you say, hey, I've scheduled my neuronal updates, now I want to change the weights, those edges in between neurons, and then you do an M step, and you can update the feedback pathways and the forward pathways, or you don't have to do it. There's a million different flavors of that. But really, if that's all confusing and annoying, I would just turn your attention to the very top left, the variational free energy, which is just the objective function. And it's a really, really easy function. Now, its derivation is really complicated, and I'm not going to go into that. There's a lot of assumptions you have to apply mathematically, like a Laplace assumption, and then assuming things like Gaussian residual errors that I'm not going to go into. But again, it does lead to a very simple cost function under certain conditions. That is just basically a plug and play kind of distributional energy. So if you know anything about energy models, one way you can equivocate it to is things like what Jan LeCun does, or Jan does in energy-based modeling. So I'll just show you visually, and I actually believe I don't even have the equations mostly on here, so I think I stripped away most of the math for the sake of speed. But again, the free energy function is just shown to the right to remind you that if you have many layers, like big L layers of neurons, you're just basically comparing a prediction from a layer below or above with the current activity at lowercase l. And then you sum them up and you sum across dimensions, and that'll get you a scalar value. Sigma, by the way, is a precision or the inverse of a covariance matrix for Gaussian stuff. But just don't worry about it. It can just be a scalar value that we set to something like 1. So what is the process of predictive coding? So I can kind of wrap up my little crash course. Well, let's say the gray states, and we're just going to pretend we have one neuron in multiple layers. These are the state neurons or the deep pyramidal cells, and they are going to try to guess the activity value of another neuron. So while you might not be able to see my cursor, I don't believe I should assume that, the gray circle at the very bottom of the slide is trying to guess the gray circle in the middle of the slide, and the middle circle is trying to guess the gray circle at the very top. So they're trying to guess each other's state or value in parallel, and they happen simultaneously. So already you have parallelism because these neurons, which always have a state, and that's very important, deep neural networks don't really have a state, they instantly transmit predictions based on whatever's going on inside of them. It could start with the value 0, it could be a random value, it could be initialized due to context. They try to guess each other's values, and that's all they do in the very first step. That's hypothesis generation. Whereas in a feed-forward network, you'd have to do a chain of computations, and every layer doesn't exist until the layer below does. So we make our predictions, we move on to the next step, and this is where we calculate our errors. So those orange diamonds are the superficial pyramidal cells, and they just basically compute the difference between the prediction that went inside of them. So the little diamonds are like depositing a prediction value. And then the little circle is saying, hey, take the current actual value and do a subtraction. And that's really all that's going on in those diamonds for this particular model. And we compute the errors in this step. So it's just subtractions. And then you say, great, I have a subtraction or a difference at every layer. Notice at the very bottom, there's no diamond because there's nothing below the bottommost gray circle. So we only need to really predict the top and the middle neurons' differences. Then we just transmit those values back. There is a little bit more to that neurocircuitry, but the idea is that we just multiply through a different feedback pathway, and it's a very short feedback pathway. We transmit the errors back to the original neurons that made their predictions, and we basically just say, hey, change your internal state, so that way when you make another prediction immediately, you'll be a little bit better at guessing what that neuron's or target neuron's value really was. To the bottom left, I'm giving you a little bit of neuroscience description of what's an inhibitory and excitatory synapse. We don't need to really worry about that right now. The idea is that we are going to correct our states given those errors that we pass back along feedback pathways. And then you're done. You've done the E step or the expectation step of the EM algorithm. You're going to do this several times. So let's say I give you an image. You're going to process it like an animal or a human does. You look at it for a period of several milliseconds. That's why I showed ordinary differential equations that you can look at the slides later. Usually for a period of milliseconds, you simulate that amount of time, you let the neurons settle to their values, and then the next and last thing you need to do is the M step, or the maximization step, where we just update the synapses themselves, which, by the way, are the little arrows that carried the predictions and the ones that carried the errors backwards. So the little black arrow with the diamond and the little black arrow with the circles kind of carry, not the dashed ones, basically are the synapses that we need to adjust. So we just changed them. And that's why I highlighted them in red for you. Instead of calling them something consistent, I just called the forward pathway W, the backward pathway V. And by the way, any one of those edges, since we're only modeling one neuron in each layer for this toy example, those are the synaptic junctures, right, between two particular neurons, the little gap, and we are modifying those neuromodulatory chemicals. You change basically the synapse, and then you process another data point, a different data point or a different sensory stimulus. You can do this in batch mode. A lot of the tools of deep learning can come back into play if you want, and you can construct ever more complicated architectures. A nice reference below is this is basically a version of dynamic EM, and my friend Carl has written at length about it. I'm not going to spend time here. You can make these equations more complicated and model other interesting properties of neurobiology, and you get more powerful generative models. You can also build ever more complicated visual processing systems. My PhD student Faiza, they're shown to the bottom left of the slide, or your bottom right maybe, basically has reproduced some of my friend Raj's work. And you can see at the very bottom the receptive fields that are learned when you learn a very specific patch level model of predictive coding. I'm not going to go into how this is constructed, but this is much more akin to how your visual system processes information. Really, to wrap this up, what does this framing really buy you? Well, you can do some really cool things, and I have, the NAC Lab and friends. The friends have shown a lot of interesting work on how predictive coding is essentially an approximation of backpropagation of errors. So under certain assumptions, you can actually recover all of deep learning. So deep learning is really like a subset of predictive coding. Predictive coding does more, and that's an interesting thing for you to read those references. You get for free a generative model. I'll show you some of the models in the mini talk that I'll give a little bit later today. But you can build a generative model with basically the thing I gave you a crash course. Now you're all experts in predictive coding. So you can basically build it. There's variations to the architectures I'm not going to go into, but you can read the work that's referenced in this slide, and it kind of gives you like a taxonomy of all the different kinds of predictive coding graphs you can build. You can build very complicated graphs that start to model things like the connectome of an insect brain. And it's kind of interesting. And so I defer you to reading my friend Thomas's work there to the left, learning on arbitrary graph topologies. So to conclude, you might say, well, great, I want to build this, and I really don't want to build everything from scratch, because it certainly sounds like it's decades of work to turn the neuroscience into machine intelligence, and you're in luck. We have NGC Learn. This tool has existed for like 7-8 years. It used to be in TensorFlow. It's written in JAX. Again, one final shameless plug in my wonderful dev team, which are my PhD students, and my good friend Ankur Mali, who's to the left of my picture there, if you know who I am. And the idea is that we kind of have maintained this tool, and we, have worked with some very brilliant programmers. My students are quite wonderful and very dedicated to this project and very responsive to support. I'll probably shamelessly plug this one more time later, but it's all written by humans. We are, basically written by humans, maintained by humans. So, and we really, have put dedication to this library. It's for neuroscience, but it's also for machine intelligence. And with that, I conclude. I'm a little over. I apologize to Alexei, but with that, I hopefully you have a crash course on predictive coding. Oh yeah, and I had a bonus slide, but we don't need that.
Any quick questions for Alex while we have him?
Let me get you a mic so that you might be able to hear it. I haven't actually tried the mic yet today. Hello? Okay.
Keep it on.
It's on down.
We could just drag people up to the front.
Yeah.
Speak to that.
Yeah, just speak in the back.
Okay.
Not sure where.
Hi, Alex. My name is Polan. I'm a huge fan of your work. I knew back when it was called Nodes and Cables, and yeah. So, but my question was, with predictive coding, one of my concerns was that you're trying to encode errors, and so the coding is now representing errors rather than representing content. Is that something that you observe is happening? And second part of that question is, I know you mentioned sparse coding, so I think you're familiar with Jeff Hawkins's Numeta's HTM, and I want to hear your views on how the sparse coding emerges in NGC and in your work, and how that relates to sparse coding in HTM.
Yeah. Thank you for those questions. Those are very fun ones, and ones I might not have enough time to go into all the depth I'd like. But yeah, NGC Learn, and it's still there. I mean, I think we still refer in the docs as the nodes and cable system because we still have nodes and cables. It's just kind of hidden inside the compiler called NGC SimLib. And if I ever get my PhD student Will to talk to you, he could talk to you hours and hours about how the nodes and cable system kind of really works. So yeah, I'm glad that you're familiar with it. That's like the old TensorFlow lingo that we had. But so to unpack your question, your very first one was about coding error. And so, yes, it is basically that you are message passing your mismatched signals into your particular neuronal values. By the way, you can design very interesting architectures that, for example, have context-dependent nodes. And I want to comment that you don't just need to adapt states only with errors. You can actually build systems that are like conditioned on some other information. And usually that just involves constructing like another synaptic pathway that projects information into those neurons. I'm not going to go into that, but there are ways to build hybrid predictive coding systems. But in the end, yes, you are essentially saying that I want to manipulate the state of each layer. And the only way that that state's going to change is basically through those encoded predictions or those message passed errors, sorry, that go back into the state. And I want to adjust such that I am better at predicting the sensory stimulus that I have. And I think where the content really starts to emerge, as you can see with the Hebbian rules that I sort of very quickly covered in the M step, just basically encode in the receptive fields of the content. So you can kind of see, for example, little digit templates, and I'll actually show in actually one of my first slides in the next 10-minute talk, you can see, for example, little digit templates. And then other neurons serve as a command control structure, in my experience, that learn to turn off and turn on these little templates, and they arrange them in like a linear or a nonlinear superposition to construct the sensory stimuli that they want. So in a way, the content's kind of like indirectly coded. But yeah, it is message passing errors, and it seems to work pretty well because then we start to connect it back to the neurobiology, which I'm not going to go into. There's a huge controversy and debate in neuroscience about whether predictive coding actually captures everything about the mechanisms of synaptic plasticity and neuronal dynamics that I'm not going to touch right now. But again, it's a wonderful place to be because the debate is still open. And again, there's also nice connections too in terms of the Bayesian interpretation. So actually, I hid all of that from you because that could take a very long time, but there's the Bayesian priors and posteriors, and you can kind of view the model as a generative model. Alexei might touch on that, but there is the prior belief, and we are essentially modifying our beliefs based on our predictions and kind of constructing a hierarchical generative model. And so in a way, you could argue the content is kind of coded through the beliefs and the priors that you impose. So I'm not going to go into that because I just realized that's a lot more jargon than we have time for. That connects us to your second question, though, about sparse coding, which does have the idea that we have, for example, a prior distribution that we impose over all the layers. For the audience that might not be familiar with what that means, basically you just constrain each layer of neurons or globs of neurons in these predictive coding architectures to say only a few of them can fire. Which also connects to, and I know of Hawkins' work and MeTTA and hierarchical temporal memory, HTM. I've read all of those when I was a young little grad student, and they're very interesting. And thousand brains theory, or thousands brain theory is very interesting as well. And I'm a fan of the sparsity that comes from that group. And so, really, at the end of the day, you get sparsity through the constraints that you impose in the neuronal dynamics. Again, I did not show all that math, but the idea is that you find out, and again, one of the models I'll show in the next little 10-minute thing later, you see only a few neurons ever fire at any time. So you get extremely sparse systems that emerge from essentially the constraints that you impose biologically on the neurons. And so that's how sparsity ends up emerging, is that you get a competition-like effect across these neurons, whether it's through a distribution or, like in my lab's work, for example, when you add synaptic weights or synaptic connections between neurons in a particular layer, you will find out that this actually creates a form of, hey, only a few neurons are supposed to light up in response to a certain concept, because the principle of sparse coding is very much in here, that you only need a few components that you arrange in some linear or nonlinear way to reconstruct the sensory stimulus that you're receiving at any input. So either through structural or distributional constraints, you can get some extreme levels of sparsity, and some things that we measured in, for example, the old Nature paper we had many years ago, you get things that are somewhat similar to the levels of sparsity you see in brain-like systems. And with that, I'm going to stop because I'm sure I still worry that I'm eating into Alexei's time. But that was a really good question. And again, I highly recommend digging into the surveys. We also have the surveys I had earlier talk about sparse coding. I know Bruno Hausen, Bruno's work was really good and inspiring. And if you just stack a bunch of those models, you sort of get almost a sparse predictive coding system. NGC-Learn also has a tutorial on sparse coding and some of these things for those that are interested in constructing extremely sparse systems where basically most things are turned off and only a few things are turned on. And that's very useful for neuromorphics. So thank you.
Thank you, Alex. That was wonderful. All right, we will move on to Alexei. Thank you for joining us, and we'll see you again here in a moment. Alexei is going to talk about probabilistic modeling perspective.
Yeah. Hi, everyone. Again, my talk will be not precisely or not at all on predictive coding. And while preparing this presentation and trying to fit into like 20 or 25 minutes, I understood that it will be impossible to go into details. So I decided to keep things high level. So the presentation will be quite simple and possibly short, but I cannot promise this. But I still hope that the notions I will outline here are useful for predictive coding in particular. So we will talk about hierarchical probabilistic models. And I would like first to start with a distinction between discriminative and generative models. This distinction is quite vague because the model structure can be different, and the objective function can also be very different. But if we consider just very basic cases, then a discriminative model tries to predict some outputs based on inputs, while generative model tries to model the whole distribution of inputs and outputs if there are outputs, and if the model is a purely unsupervised learning model, then it will just learn the distribution of inputs. And what's important, it's typically not just a distribution, it's a computational way of sampling access from this distribution, and distribution can be even implicit. But in the best case, it can also both sample and provide the whole distribution. And why this distinction is important? It's because when a discriminative model predicts outputs, it just tries to separate regions. Well, if it's a categorical model, if outputs are real valued or tensors, then it's a little bit different, but the idea is the same. It doesn't try to understand how data points are distributed within the regions. It just constructs the features which are useful for predicting outputs, for discriminating between them. And this is also reflected by the training objective. It should be noted that optimizing, say, probabilities of yi given xy on the training set is not what really needed in machine learning, because we need to perform predictions on new points. And that's why if you consider a discriminative model which just tries to optimize posterior probabilities of outputs given inputs on the training set, then it's just a simplification and limitation. So discriminative models can do something more complex in order to make predictions on new data points. In general, not typically in practice, but well, of course, different regularization techniques are applied, like dropouts, and so on. In any case, it should be underlined that what the model is trained to do can be different. And in case of a generative model, when we have a downstream task, we still want to describe the distribution, joint distribution of inputs and outputs. And in a more simplistic case, we can try just to describe distributions of inputs and then predict outputs based on some latent code. But discriminative models are directly trained to predict outputs on new data points, and it should be obvious then that generative models are weaker for predicting y, can be weaker for prediction y, depending, of course, on many details, like if we are doing some transfer learning and so on. But in general, if you take two architectures of the same power, of the same structure, like deep neural networks, and you train a generative model like autoencoders or whatever, you will get weaker features for predicting y, predicting outputs, unless you do some follow-up fine-tuning. So you should not expect from generative models to outperform discriminative models without, of course, some tricks and so on purely discriminative tasks. So generative models should be applied for the tasks they are trained for. Okay, and the next thing I would like to talk is to discriminate between multi-layer and hierarchical models, because it's also an important difference. So if we consider any prediction task, then typically we need some complex processing of inputs or of latent code to generate outputs or to generate observations, and this processing is performed in multiple steps. It doesn't necessarily implies that we are doing a sort of multi-layered network, artificial neural network processing, but even if you consider traditional algorithms, they will also do a sort of data flow processing. When you have some inputs, they're somehow combined on multiple steps, and so on. And in general case, each next generated or computed value is based on all the previous values, but in a simplified case of multi-layered neural networks, this of course will give us a dependence just on a previous layer. So multi-layer models deterministically compute intermediate results, and what is also important that the objective function with which these models are trained also depends only on inputs and outputs. While hierarchical models are different in that the intermediate variables are also considered as a target for optimization. If we consider probabilistic models, then we can say that these intermediate variables are also random variables, and they participate in the loss function. In the case, what's interesting, it is possible to construct hierarchical discriminative models. In this case, each next layer of a neural network will have neurons which activities are not fully determined by activities of the previous layer, but we can say that we have a probabilistic distribution over values centered around these predicted or computed values. And in this case, such a hierarchical discriminative model will have a different objective because we will need to optimize both the probability of the output and the values of intermediate variables. But it should be noted that this model will still not try to generate observations. It will not try to generate inputs. So we should be aware that if we just introduce such variables which can be modified in a discriminative model, then it will not instantly become a generative model. It will construct some features of inputs, but these features will still serve for one reason: to predict outputs and to predict next layer. So I am not an expert in predictive coding, but I saw a lot of works in which predictive coding is applied to discriminative models, and the structure of models is not changed at all. So it's still a discriminative model which takes inputs, constructs next activation values of next layers. It of course performs optimization, for example, in expectation maximization way, but in my opinion, it would be a mistake to think that such a hierarchical discriminative model can learn representations of input data. It will learn features which are extracted from input data, but these features serve not to reconstruct inputs, but to predict outputs. And it should also be noted that this objective function is different from what we had in purely discriminative models. In the best case, it means that we have just some additional regularization. In the worst case, it can lead to worse predictions of outputs. Another possibility is multi-layer generative models. And in variational autoencoders, in generative adversarial networks, it's actually the case. We have only one layer of random variables. It's a highest level latent code, and inputs or access are constructed deterministically from these random latent variables. So we apply all these transformations in a deterministic way, and only when we arrive at the lowest level, we can add some noise. So we consider that x, final x, is sampled from some distribution centered around some very nonlinear transformation of the highest level latent code. The problem is that all information about inputs should already be presented in this latent code. And only nonlinear transformations connect this latent code with access. And of course, it's problematic because, for example, if we are talking about images, image can have noise or some small structural details which makes no sense to describe on the highest level of our network. So that's why if we are talking about representation learning, I believe that we should consider hierarchical generative models. And in such models, each layer adds some information. So we have some highest level latent code, which is sampled from a prior distribution, or which is conditioned on some cognitive system on top of it, if we imagine this. And then each next layer not just deterministically transforms this latent code, but each such layer also adds some information. If once again we consider images, then in say classical structural image descriptions, then on the highest level we can have objects, then we can have complex shapes, which then can be broken into simple structural elements, which are represented as contours, and so on. And at least each layer, we can say that, well, it's not a precise triangle, right? It has some imperfectness. This imperfectness is not described on the highest level of abstraction. It is described on an appropriate level of representation. And this hierarchical generative model is trained to optimize a full joint probability or energy, free energy, or whatever. And well, I will maybe skip some of this. And we can actually derive many things from this. We can see that in such, it actually applies to hierarchical discriminative models as well, but on example of hierarchical generative models, we can see that the objective function can be considered as a sum of subfunctions, and it is not correct to optimize them one by one, these components, these terms, because if we make a bad choice initially, which can look bad because its own probability can be higher than of other possibilities, other hypotheses. Then on other layers, we can go to much lower probabilities. So when we have some of such terms, we should optimize them all together. And it leads us to various optimization techniques. We can take a gradient from this and see that updates of the layer should depend on the previous layer and the next layer as well. And we can apply various assumptions and various implications, and particular update rules can be inferred within these assumptions, and we can assume different distributions, choose different approximations. One thing also to know that we should distinguish between the model structure, the objective function, and optimization techniques, because we can infer different we can apply different optimization techniques to the same model. Okay, so I would like wrap up my talk with an example of very popular nowadays discriminative model, which is LLMs. While large language models are considered as generative AI because they basically generate something, in fact, each next token is predicted in a bottom-up discriminative way. And this basically makes them discriminative models. And there is no attempt to reconstruct the prompt from any latent code. There is no such latent code in an LLM which contains information about the whole prompt. And the training objective is purely discriminative. So you need to optimize a conditional probability of the next token given all the previous tokens. So it goes from observations directly to the results. And all intermediate computations are deterministic, so it's not hierarchical models in a probabilistic sense. Of course, if we apply a chain rule to the next token prediction task, then we will get a joint probability over all tokens, and it looks like a generative model, so it may confuse us, but actually there are different techniques which try to optimize this overall objective, not in a greedy way, next by next token, but via sampling, say beam search, or via gradients, like in energy-based transformers, or we can even turn LLMs into a hierarchical model with the use of predictive coding. But my point is that they will still remain discriminative models in nature, because each next token is predicted directly from previous tokens. So once again, there will be no place in the model in LLM which contains information, unconditioned information about all the tokens, all the text, and it has positional structure. So at each position, it has some embeddings, but these embeddings collect information from all the previous tokens just to predict the next token. So these embeddings do not represent all this context window. They just discriminate between candidates for the next token. And the training objective is also still discriminative. Okay, I guess I can skip the last question. So in conclusion, I would like to say that discriminative models are specialized for estimating the conditional probability, and they construct features or projections of observations to differentiate between outputs. These features can be both lossy and redundant. So LLMs, while predicting the next token, will not put information into this embedding, which is not necessary for predicting this token. So they for sure can lose some information about the input text. So there is no representation of this input text in them, only some projections. Introduction of hierarchical latents doesn't change the objective. So if we have a discriminative model, it will remain discriminative even if we apply predictive coding or whatever to it. And once again, LLMs don't have objective to describe the context of the text, including both the input prompt and their own thoughts. And hierarchical generative models, while they are weak in terms of solving specialized downstream tasks, they might be needed for this. And tomorrow we will have a contributed talk on AGI conference about this in more detail. So thank you for attention.
Thank you very much, Alexei. That was wonderful. Are there any quick questions before we move on to the next section for Alexei? It looks like you were crystal clear and there were no questions.
Well, yeah, I think Alexei queued things up nicely, and much of the work we've been looking at on predictive coding neural nets has been focused on computer vision, and some has been reinforcement learning for robotics. And these are all super interesting areas. One of the things I've been trying to steer the team toward, working within SingularityNET orbit on predictive coding, is for predictive coding transformers, just for the obvious reason that transformers are doing so much amazing stuff in the world now. And when you try to port predictive coding to transformers, and there's a few research papers trying to do that now in different ways, but when you really think through hard how to do that, you do hit a bunch of the issues that Alexei has raised here in a pleasantly general way. Like, what are you really trying to get the PC transformer to do? Do you want to think about it as trying to get the PC transformer to predict the next token? Or when you apply PC to a transformer-like domain, do you want to think through the objective differently? Because, I mean, what Alexei was hinting at, among other things, is when you shift from backpropagation to predictive coding, then, I mean, it becomes very straightforward to make it a full generative model in the sense that he describes, whereas there are reasons that within backpropagation that wasn't done, right? And this gets at the more general point that a lot of the neural architectures that are used now in commercial AI are used because that's the architecture on which people could get backpropagation to converge nicely with a modest amount of hyperparameter tuning rather than because that architecture conceptually necessarily made the most sense. And the architectures that you tried, but then gave up on because you couldn't get the hyperparameter tuning and the convergence to work, mostly aren't reported in the literature, although now and then they are, but someone sort of got them to work and then no one could replicate or extend it, right? So part of the thinking here underlying this collection of ideas we're presenting is that this sort of true generative approach, doing transformer-like stuff, probably can be gotten to actually converge and work tractably at large scale if you swap out backpropagation for predictive coding. And that's really why this stuff interests me so much. I'm not as much of a biologist as Alex Arobia, who gave a great talk. And I mean, I did work in computational neuroscience for a number of years. It's really interesting. But from an AGI point of view, I don't necessarily care how the human brain does it, except insofar as there are clues you can extract there.
It works.
They get the algorithms to work better. And I think here we see some clues from biology and some clues from the mathematics of learning converging together to suggest that the predictive coding approach should have a lot of promise. Then we also have modest scale empirical results pointing in that very same direction, which leads on to some of the next talk.
Thank you, Ben. Yes, so we'll have Alex Robia back up to talk more specifically about the progress made in his lab on predictive coding to follow up these two introductions.
This is like an all Alex session.
All Alex, all the time.
I aspire.
Danielix, yes.
It's a lot of Alex. It's a lot of Alex today, isn't it? Let me.
A lot of smart Alex.
Well, smart.
That I
Oh, it's because I'm still in presentation. Okay, so now, do you see my new slide deck?
We see slides, yes. Your audio is a little bit fuzzy here. I don't know if that's us or if there's anything that you can do.
It could be on my. How about now?
Still the same. Try again.
Hello.
That sounds a little bit better. No.
Okay. I could also let me drop out and drop in because sometimes my computer acts a little dumb with Zoom. I don't know why, but if I drop back in, I think it'll be sharper. So let me do that quickly. I'll join in a minute.
Okay. Welcome back.
How about now? How's that?
That's wonderful.
It's basically my very long and a different life. I was tech desk. It's turning it off and turning it on again, I guess, is the principle, right? It's really the only thing that works. Yeah. Okay, so now, nope, wrong one. How about now? Do you see that? Perfect.
Yes.
Okay. And I still sound good, right?
Yes.
Okay. Now, I did promise you I would try to stay to 10 minutes, so let's do that too. Time myself. All right, and that way I give everyone else enough time to talk about what they want. So, hi again, everyone. Yes, there's a little bit more of me than maybe you perhaps want. Yeah, so kind of following off of Alexei's probabilistic modeling talk and then my earlier crash course on predictive coding, I'm just basically going to spend about 10 minutes showing you what you can do with predictive coding, or rather what the NAC Lab and friends have done over the last decade or so. And this is only a sampling too. Again, I strongly refer you to the survey of the last talk, and I'm sure we will release slides later so that way you can kind of poke at those references, because those kind of really give you full coverage. So this is actually a slightly now outdated, I've realized, that we have a little bit more work, and I'm going to show you some cutting edge frontier stuff from this year, if I can make myself go fast enough. But we can kind of break up the work from the NAC Lab and those that collaborate with us into kind of 4 quadrants. And we'll start with we'll start with image processing. And again, this is a growing body of work, and there's still a lot of space to grow. Again, as Ben mentioned earlier in introducing my talk, SingularityNET is interested in trying to scale things up, and I think that's a very important problem space to investigate. And yeah, even though there are the biological nerds like me who care what the synapses and neurons do, there's a lot that they bring to the table, in so much as trying to construct architectures that generalize in ways that maybe deep learning cannot. This was the diagram I sort of hinted at and promised earlier when I was giving you an idea of predictive coding, and also in answering one of the questions about receptive fields later on. But the idea is that what we did in the Nature papers, we also probed what was the structure of an example of a trained predictive coding network. So what I like about this diagram is if you look above the 0, the digit of 0, you'll see the first row. Those are receptive fields, or really, if a neuroscientist was in the room, they're called projective fields, to be perfectly accurate. These are the little feature templates that were extracted by a very sparse predictive coding structure that we had proposed in this paper. And it kind of learns these little templates. And what was interesting is then in the other 2 rows, the ones with the red squares, those are latent variable layers or hidden neuron layers, whatever you want to call them. And what we found out was it looked like that they were constructing like a latent command structure. And so what these architectures tend to learn, particularly the generative ones that are unsupervised and essentially learn to maximize a P of X given Z, they learn to kind of superimpose weighted versions of these feature templates. And so what's really interesting is that bottom 0 is actually a confabulation or a reconstruction from these particular red neurons that kind of go back from the top through to the bottom layer of the predictive coding network. You traverse the synaptic connections that are excitatory or those that are positive valued, and you can kind of compute these little weights, and then you sum up these little templates and you get a digit of an actual 0 that appeared in the data distribution contained in the data set used to train this model. And then what was really fun is that because I have a fondness for generative models from the older days, we would sample these confabulations. It's also from the lingo of Boltzmann machines and harmoniums, which I used to work on. And so you can kind of see a bunch of 0, like the Nemnis digits. These are samples taken from the model, or you'll see kanji digits or Japanese characters to the far right. And this is the very, very bottom row of the slide, or clothing or silhouettes. So this was like binarized data that we trained on for this very old model in 2022. So I thought that was really interesting. Now, of course, if you want to deal with things that are a little bit more complicated than, digit recognition images or OCR problems, and you want to work with natural images, you sort of have to generalize the predictive coding structure a little bit further. So you need to impose like a convolutional inductive bias. And so you can kind of do that. And so we proposed a little bit later after that work in 2023 with collaborator, my good friend Ankur, we constructed what was called convolutional predictive coding. And it was kind of one of the first like grounding formulations of how do you integrate these convolutions and sparse convolutions in a predictive coding structure. This was also one of the interesting works that we showed out of sample generalization. And there's a lot more detail that I recommend just reading that reference, where we were able to show that you could reconstruct data that you've never seen before, like completely different natural images by training on CFAR. We could do SVHN and vice versa. The other thing I particularly liked, just because it tickled my neuroscience fancy a bit, and classical knowledge was the receptive field, sorry, the feature maps that you see, that digit 4, actually going from the bottom towards the top, you see feature maps emerge in these hidden layers. And what happens is you go progressively deeper into the architecture, they become lower and lower resolution. And classically, that's called the image pyramid. What was wonderful was we didn't do anything to bias the model to learn the feature pyramid, which has some biological connections. It just emerged naturally, which was very fascinating and a really fun conclusion for that work. And so it's interesting the types of things you get when you construct things from a biological perspective. Would these feature maps be interesting or useful? That's a subject for machine intelligence. Here's the math for it. I'm not going to dwell on it, but obviously you need to use the convolutional circular convolution, or you need to use deconvolution or transpose convolution. There's a lot of interesting mathematics to construct this, but the dynamics are almost the same. You just now don't do affine transformations with dense matrices. And then, of course, my good friend Tomaso and friends have also shown that these architectures or structures with convolution can scale up to complicated data sets that are even competitive with backpropagation-based networks. That's what the CNN is on, with BP, that's backpropagation, and PC is a predictive coding version of that architecture. So you start to get things that are a little bit more on par, kind of important to communicate to the machine intelligence world. Now, moving away from natural images, because there's a lot you could talk about that, you might be interested in, well, what about videos or sequential streams or things with temporal structure? So actually, this was even older work, going back as far as 2017, 2019, where we showed that, for example, you can build a predictive coding temporal generative model. And basically, we played with things like bouncing digits and the like. The idea is that this thing has to now process video frames for a particular stimulus period and kind of move on to the next one. And you can construct some very efficient guess and check kind of predictive coding structure. It's similar to what I gave you the crash course earlier, except now we have to deal with recurrence. The really fun part that I particularly liked about it, and it's hinted at the slide, is you don't have to train it with backprop through time. Backprop through time is probably my lab's most hated algorithm, not because it isn't a useful thing for training language models and when it was recurrent nets, but rather that you have to unroll the entire graph over time. Brains don't go backwards in time and create a time machine and unroll yourself into a super brain that you then update and roll back up and do this forever. That'd be extremely inefficient and wonky. So this is an online architecture, which is really, really useful. And then we showed that it could do things like continual learning for sequences, and it actually outperformed all the other biological temporal models that we compared to. Language, it did pretty well. It beat out the biological models. It couldn't quite match backprop through time, though, at the time when LSTMs and GRUs and those likes were still in fashion. And then, of course, what's really cool about these temporal generative predictive coding models is, you can then confabulate sequences that still incorporate the physics. So this was the bouncing ball problem, adapted from my friend Jeff Hinton's work on sequential Boltzmann machines and temporal Boltzmann machines. So we reappropriated his benchmark and kind of showed that you could learn the same thing with an online predictive coding model. Now, if you incorporate the convolutional stuff that I talked about earlier and the temporal modeling stuff, you can actually get a synthesizer that, again, my lab works in Neural-Robotics, so we're particularly interested in, things that pick up blocks and do very, very simple tasks that are actually super hard if you want to do them, from scratch and learn them in an online, biological fashion. So it's really cool. To the left, I'm showing you these little samples of fantasies from a convolutional temporal predictive coding model. And again, you can use this to help guide, for example, a robotic controller. To the right, I'm not going to go into all those details, but you can also build predictive coding models for graph topologies. Again, my friend Tomaso and others have shown that you can actually learn some pretty competitive models with predictive coding. And again, we already know this from the other talks, so I'm not going to steal their thunder, but you can also do transformers and language models with predictive coding. It just depends on the type of distribution you impose. There is a trick to that. But again, I just recommend you read some of these related bits of work. And then I'll just quickly skip over this, but you can also do things like continual learning. Again, the problem in deep learning is catastrophic forgetting. You train a neural network on one data set, then train it on another immediately after. It forgets everything it learned on the first one. Humans don't do that. We don't forget how to breathe when we learn to play the piano. So, the idea is that we have a complex structure that learns through memory. So we built sort of like a predictive coding model that outperformed actually a lot of even a humongous array of continual learning benchmarks at the time. This was, again, many years ago. Continual learning has now progressed to transformers, where you basically just pre-train it. Still think catastrophic forgetting is an unsolved problem, but that's just my own humble opinion. And the final little bit of work, I am a little over my personal time here, but the dynamic cognitive control or reinforcement learning. I'm not going to explain all this architecture to you, but you can basically, once you accept and commit yourself to predictive coding circuitry, as Alexei actually really nicely presented, either from a discriminative or a generative point of view, you can use these as little building blocks to now build cognitive architectures, which is also another leg of work that my lab has done in a variety of contexts, including through old papers that we presented or submitted to AGI in the past. And so you can build, for example, this one is one of the more modern ones. You can build a robotic controller that basically takes a generative world model and a motor control model. And if you accept that, you can do motor control through a predictive coding circuit, you can then add a policy and do continuous actions. And then what was really fun about this work is in this structure, when you do biologically plausible reinforcement learning, you can now impose a prior preference. I work a lot with my friend Carl and others on active inference, which is just a process theory for biological reinforcement learning. And it allows you to deal things with the hard problem of RL, which is what I would like to solve, this problem of sparse rewards, which is you do a lot of things in a row, and I only tell you at the very end of a game or an episode, yes, you did well, you did bad, now you got to figure out how to do credit assignment through time. So not going to go into all of that, but there's some really fun architectures that are motivated by cognitive science, because I also hail from that world. So you can build little working memories, which is very useful for solving different RL control problems. And of course, what's our grand vision? So this is sort of Cog Engine, which is cognitive neural generative coding for active inference. This is our general cognitive architecture that basically has different modules inspired by the common model of cognition. My friend John Laird and others in the cognitive science community have kind of sketched a blueprint of how your mind is kind of organized into different memory systems. And we want to show you how to build such a system through predictive coding. And we have done little versions of that model. Like, for example, we can do procedural RL, which is actually a really hard problem, or was at the time. And so this is a little predictive coding cognitive control agent learning to navigate this environment dynamically, which I always thought was a really fun problem. And of course, I'll just show you a little robot. We also did some stuff we've presented at the conference known as International Conference on Robotics and Automation. So you can kind of see the agent from left to right getting progressively better. This is one of our cognitive control agents. What's kind of funny is that agent to the left, when before training, it kind of just flops around for a very long time. I'm not going to dwell here, but the final kind of conclusion is you can also convert all of this to the neuromorphic level. And we have shown that you can build a very intricate neuroanatomical model that, neurons in the brain actually fire pulses, not real values, which are extraordinarily sparse. I believe this is where the future lies, is neuromorphics, but that's a personal bias. But that's where you get the energy efficiency. And that's something we could discuss later, but you can do continual learning. But I think I'll just end with some concluding remarks. I am over my time, I apologize, but there are some problems even with predictive coding itself, since I'm always looking ahead and trying to hedge my bets as to find what is the most biologically plausible, but yet most general kind of architecture, learning algorithm. So I look at a bunch of other things beyond predictive coding and maybe sometimes bring it back. So one thing that is really funny about predictive coding, and this is what this work, the very recent work, my good friend Carl and Miraj and I kind of propose an architecture where we flip predictive coding upside down. While I'll always have a fondness for generative models and decoders where you start from Z and go to the input, that also requires you to learn complex things about the environment, and a lot of that information is distracting. Maybe it's better to form some sparse, clean representations of the environment with only an encoder and no decoder. And there's a lot of interesting biological evidence motivating this direction, but that would mean that you can no longer predict pixels. You have to predict something in a latent space. Jan has also done work like this, if you've heard of VJEPA or JEPA, which are these joint predictive embedding architectures that do self-supervised learning. So basically, Carl, Raj, and I converted self-supervised learning and deep learning, which is kind of a growing niche. And we showed you how we're the first to show you, how you do it in biology. And so this was a really interesting model, was inspired by central and peripheral vision in the eye and how we do saccades and glance through an image. And what's really fun, just without going into all the wonderful actual, visual neurobiology that motivated this architecture, you can see my love of receptive fields and showing you what the architecture learns. That plot to the top, I think, is a really interesting one because this is where you can see the sample efficiency come into play when you do information foraging through an image, looking at little parts of it and building a global representation. And the way that we did our self-supervised objective function allowed us to avoid the things like negative samples and all the other kind of gunk that goes into a lot of modern day self-supervised learning. And we could get, high predictive accuracy in a self-supervised architecture as low as like 100 samples. Like that red line is decreasing a little bit, but it is outperforming backprop by quite a bit. So this was one of my favorite results. Of course, it is just on MNIST. Whether this result holds on more complex data is yet to be seen. It also does happen on Kanji MNIST or Kayazuka MNIST. I won't dwell on this. This is just to say that you can do self-supervised learning with spikes and even combine that with predictive coding, and then you get some really nice neuromorphic stuff. This was a science paper we had last year or 2 years ago that kind of showed you, how to go about doing that. There's a lot of interesting questions. I won't, since I'm over my time, I won't dwell on them, but you can look at these slides later. These are some open things for us to investigate. The only thing I'll highlight here is in the bold italics, cognitive architecture prior. This is sort of my way of saying that I don't think that we can just build big monolithic predictive coding architectures and hope to solve complex cognitive processing that humans and animals do. I think you need the modularity of the common model of cognition. I come from that kind of classical tradition and firmly believe we need to incorporate that prior in viable, flexible neuronal circuits. But again, at the end of the day, this kind of lines up a little bit with Ben's view on why comp neural can be helpful, but don't go too crazy with it. I think Albert's quote, make everything as simple as possible, but not simpler, is the way to go for how much biology you want to bring in. Again, this was just to remind you we're the NAC Lab and all our wonderful friends and collaborators over the years. Please, again, check out our NGC Learn library. There's also a lot of other tools and modules that go with it. I think I'll close, and I'm 8 minutes over, but the NGC Museum. So I'm a huge fan of museums and reproducing classical work and kind of showcasing it. So our museum right now is a little bit small, but these are models that you can actually just run that reproduce historical work. There's also a segment for our lab. The only thing I like to highlight, and you can kind of see my wonderful PhD students that do development with me and maintain the museum as well. We have spike models and real valued models. And what NGC Learn is all about is to enable new students and researchers coming into the field to build their own models and do research and simulate things at scale. So we're very efficient and optimized library with lots of good things coming down the road. Last thing I'll just say is community contributions are very warmly welcomed. We would love to feature your work if you use NGC Learn because it's great to reproduce scientific results so that way future generations can kind of build on what you've done. And so I think with that, I will stop my very, very long over talk. I apologize and hope you guys check out NGC Learn and what the NAC Lab produces in the future. Thank you very much for having me speak.
Thank you so much, Alex. That was wonderful.
So any quick questions for Alex on all that?
I have a question.
You might have to go to the front. Sorry.
The question being asked, I can't hear it.
It's coming, it's coming.
Sorry, I picked up to the front of the room.
No, I just want to make sure I'm not hearing you or hearing you.
Thanks for the super exciting talks. Really, really interesting. One of the things that you didn't talk about with the conventional feed-forward neural networks, it's not just backprop that was the big magic trick. It was the regularization techniques like dropout that allowed you to do the insane, which is to have a huge number of parameters, which would normally overfit like crazy, and get this generalization. And this has basically allowed us to do things like not the toy examples like MNIST, which are very small models, but to do large language models, for example, right? And to be able to do it in a computationally efficient way with GPUs, because it's not very costly to do those little tricks, for example. And with MNIST, you can get away with a lot of things. You can do you can get really good results with a simple energy-based model or something complex like capsule networks or something like that. But for these real hard types of things, like dealing with natural language understanding, open domain, or even like graph learning, GNNs, they don't scale very well. For this particular type of techniques, I'm just wondering, you mentioned briefly LLMs, but in terms of I'm wondering about the computational costs of this predictive coding when you really need to do really, really large models, super large models, like the world that we live in right now, where we have models in the conventional deep learning space that are, hundreds of billions of parameters, billions of parameters. So I just was wondering how deep the research space has gone on that.
Okay, so to sort of unpack your comments, which I agree with most of what you're saying about even like the value of regularization, the tricks that give rise to the power behind deep learning today. So to be super honest and upfront, as I usually am, even with my work and presenting predictive coding, if you were going to run these neuroscience models, predictive coding being at the forefront of them on standard architectures, particularly like a GPU, it's worse than backprop. It's slow in the sense that it's slower. And why do I say that? Well, if you design, in a traditional kind of GPU, single GPU, and you run this architecture like you would a feed-forward network, backprop and the deep learning kind of structures are faster because you're just doing one chain of operations, a forward pass, and then you do a backward pass. So that is as fast as you're going to probably get unless you can make those operators quicker. Predictive coding, as one example of a lot of neuroscience models, because it's grounded in simulating time, and you would have gotten this from even my crash course that I tried to give you. Hopefully I conveyed that clearly. If I give you an image where as in a feed-forward network, you would just run it through the network and then do backprop with your objective function and call it a day, predictive coding requires processing that image multiple times. So you could say that's many feed-forward passes. Even if it's done online, you don't have to like unroll or fold this graph. You are simulating, let's say 20 milliseconds, 100 milliseconds. You're doing numerical integration. So like, for example, you're doing Euler integration for those that know that, or Runge-Kutta fourth order. And the idea is you're trying to modify these differential equations to say, I want to converge to some stable state. And then you get to do some heavy learning at certain points if you schedule things correctly. So already right there on a GPU, you are slower. And a lot of neuroscience is like that. The power, and I've had discussions even privately with Ben about this, where you can get the benefit from predictive coding, especially at scale, because right now you'd say, okay, so it's just slower. It might generalize better or do some interesting things that you don't do with, backprop-based LLMs or backprop-based DNNs. You need to take advantage of what properties emerge in these biological systems. For example, when I was showing you how forward inference happens in one step of the EM algorithm, those are parallel. So these neuronal layers are not locked like in a deep neural network. So what would be one thing is you have different computational units or core units like GPUs or TPUs assigned to a blob of neurons. So now you have parallelism. There's only like a linear speed up you could probably get, but you can chop it up by more computing units kind of allocated to different portions of a predictive coding circuit. You can also do asynchronous computation. And my friend Tomaso has an interesting paper, Incremental Predictive Coding. My lab has kind of played around with that too. And you can kind of get things where you don't need the layers to even be perfectly globally synchronized, which is biologically more realistic. But now you can do async computing for free. You get parallel computing for free across layers, which some people have tried to do that in backprop, but it's really wonky and you make weird approximations and it's not clear that it's the best approach. So you get faster forward inference per step. If you use parallelism. This other dimension I want to highlight quickly kind of relates to the question I got in my crash course about sparsity. I also think the real trick to taking advantage of biological systems like predictive coding is the fact that only a few neurons are firing at any instant. That means you can do things like extremely sparse matrix computations, and sparse matrix multiplies are really fast if you're only computing a few things. The beauty of sparsity, in case those in the audience might not know, it's zero for something that doesn't exist. And in hardware, you don't really want to compute a zero. It just means don't do it. Anything that's not zero, you compute. So there's also this beautiful set of sparsity that I think is unexploited in deep learning. And so we need to build things like, I think you use a trie or a tree architecture kind of to structure the matrix computations for sparse compute. So I think combining that with the parallelism would allow these things to scale up to massive levels. My final point, just again to address why maybe even this is interesting to look into neuro AI and even neuromorphic computing. So I think the real place where biological systems will play a role is in edge computing, where you have things like a neuromorphic chip, where you do in-memory computation, which I will touch on in tomorrow's keynote talk about mortal computation. But the idea is you have to design your neural system for the hardware that you want to implement. And that's where you get extreme energy efficiency, whereas LLMs, as we keep scaling them up in the hoping that magically they'll just produce AGI, they are burning holes in our ozone layer. I mean, they are terrible in terms of their carbon footprint. They are great energy sinks, and putting them in a nuclear power plant or allocating everything, we have like some people say very publicly, and they're grossly incorrect about this pathway. We're throwing away the opportunity to have extremely energy efficient and powerful systems like those in neuromorphics. So I think when you start to think about spiking implementations of predictive coding, now you can build them in asynchronous crossbars. And so I think that's really interesting space to go down, where you build things for analog computing, for FPGAs that are extremely low power. I think that's where the biological systems are going to shine. If you're just going to put them on a GPU, I mean, those were built they're even optimized these days for backprop-based DNNs. So I think that at the end of the day, they're useful for simulating things on a von Neumann architecture, but I think we also need to embrace a bigger picture in biology, which is what is the substrate that we are executing predictive coding on. And I think that's where the big future will be, but it's probably over the next several decades if we eventually leave behind some of the deep learning ways we do things. And I think I'll stop there as I'm ranting a bit.
No, thanks a lot.
Thank you.
Thanks so much.
Yeah, thank you for having me and speaking.
So I want to briefly give a complimentary view on your question, because I think from a biological simulation view, that's a very accurate and on target issue. From a sort of near-term AGI view, you can look at it differently. I think Alex's mention of a trie structure for sparse updates is interesting. We heard this morning about MORC, which is a trie structure, right? I mean, it's a multi-rooted prefix tree, which is intended precisely for sparse updates, right? And so as an example of creative things one could do, there's something called the waveformer, which is a transformer that takes some of the internal layers, builds a wavelet transform from it, and displays this wavelet transform out among a number of different layers. Now, if you take a waveformer, this lays very, very neatly onto MORC, because I mean, MORC is these paths, and the paths will basically go through the wavelet coefficients from the coarse grain to the fine grain. So a waveformer is an example of a transformer architecture. It's sparse in a specific way that maps very neatly into the MORC pathmap architecture that we have in Hyperon. Now, predictive coding allows asynchronous updating across a network, which, for example, could be done by concurrent processing across multiple cores, right? So if you take a waveformer, you modify waveformer to use predictive coding, right? Then you put that into our more like super efficient trie data structure. You run this not on a GPU, but on a multi-core machine. The multi-core machine can then update all the parts of that trie asynchronously in parallel, and predictive coding is okay with that, right? So that illustrates an alternate approach to scaling things up. We're using multi-core and you're using MORC, but you're using a particular variant of transformer that's well suited to this particular efficient data structure, right? And so one of the things that Alexa highlighted is we have a whole software stack which is very well fitted for backpropagation now, and in obvious and less obvious ways, right? Like the obvious ways is, okay, backprop wants you to synchronously update a network, and that naturally translates into doing a big matrix multiplication, right? But also, even now, the way memory is managed within the GPU is highly attuned to backprop. So indeed, if you just plug a PC network at the top of this stack, you're going to have performance issues relative to backpropagation. But if you rethink the hardware stack, okay, it could be multi-core, CPU, it doesn't have to be GPU. And then you rethink what data structure you're using. Well, it could be MORC instead of big matrices, right? If you rethink all the parts of this stack, from your network architecture and learning mechanism down to what hardware you're using, I mean, then it's much less obvious how the scalability plays out. And one thing I found when first getting into this space seriously in the last year or so is, I mean, people just haven't been running those large scale experiments. I mean, it's been driven by fantastic academics and PhD students who are running modest scale experiments and publishing papers. Like no one, it's not like people have been trying to scale up predictive coding on huge supercomputers and huge data sets and doing massive hyperparameter tuning and failing. I mean, the experiments haven't really been run, right? And so we're pretty much gearing up to running those experiments during the next 6 or 9 months, let's say, by taking existing academic work, unhacking some of the code there, starting to run it on slightly larger. And I wasn't speaking of the code from Alex's lab by unhacking, really. It's mostly other people doing PC transformer stuff, which hasn't been his lab's focus, right? And then trying modest scale and kind of gradually scaling up. And that was done for backprop over a significant period of time. We're trying to do that over a shorter period of time with predictive coding, but to some extent, there's still a learning that has to happen from taking from the existing academic stuff, scaling up a little bit, seeing what works, scaling up a little more, and seeing what works. And we're trying to compress that process in time as much as we can by introducing various clever things along the way, and as much as possible, trying to make those clever things sort of grounded in broad theoretical principles rather than just being hacks. And that I hope is a good lead into Daniel's talk.
Thank you, Ben. Thank you, Alex. Thank you, Alexei. I don't think I could have.
The grand finale.
I don't think I could have asked for more lead in anticipation of build up. The main purpose of the main thing. So when I gave this talk to Matthew, it took 42 minutes. So I cut it down a little bit. So it should take maybe 38 now. I'm just kidding. I'm going to try to go really fast. My main intention was less about absolute understanding than like just get you guys excited and share some of the imaginative possibilities that got me excited about predictive coding when I learned about it literally a year ago when I saw Alex's talk, and I haven't really stopped thinking about it since then. So I'm going to talk about one of many concepts that I've been exploring about unlocking scalable continued learning with predictive coding. So as we've sort of been dancing around and alluding to, I've chosen a focus question to guide this kind of inquiry. And the focus question could be, how do we integrate memories into neural nets in a scalable way? And the focus application is, I'd like to train GPT-5 incrementally. I'd like to add new chunks of data every day and not have to retrain the whole thing. That doesn't work. IID, batch, et cetera. We'll go into it. Some typical approaches to integrating memory, differentiable memory units, op-field nets, transform retention layers, heuristic hacks, graph and other things that are, even worse. The question that occurred to me was, well, maybe PC lets us look at this differently. Maybe because we've decoupled the backward pass. We're doing things fully locally, like all the computations in PC are local in space and time. Does that let us do something differently? So here's a thought experiment that I've been playing with for a minute. Thought experiment is, what if I have a deep neural net, kind of predictive coding deep neural net thing. Let's go mouse here. Sorry, guys, it's kind of laggy. You've got this is a predictive coding stack of dense layers, some deep neural net, and now I want to integrate some kind of memory. And the memory mechanism could be arbitrary, could have the same kind of update dynamics. It could be just a key value store, could be hypervectors, could be whatever. So one way we could combine these is to think about adding an attention layer. And this is a type of computational topology I haven't seen in the predictive coding literature, and that might be just because I haven't read as much of it as there is. But the idea here is that we let each branch sort of make a prediction for what we think the target output is supposed to be, and then see which one's better. And we're doing this in this predictive coding loop. We've got this multiple sort of inference steps where each node is sort of updating itself to be better and better. And this annealing process will sort of let one of them settle it and win out. So you sort of do this winner take all thing on this layer. And what's nice about this is that this adds some composability, right? Like, because you can add new branches, or you can swap them in and out without impacting the performance of the network. Like, you won't make it worse by adding a new one. It'll just be ignored if it's not good, that particular thing. The branches can have wildly different learning mechanisms. All they need to do is be minimizing the same local error metrics when you update the weights and the activations, but that leaves a very wide design space of what actually goes on inside the layers. And all the math that Alex and others were showing, is just one example of how to do that. But you can do this on symbolic, do this on metagraphs. There's all kinds of things you can do. Another way to view this is that you're effectively gluing two different energy landscapes together. You've got an energy landscape sort of modeled by the sort of typical, multi-layer dense perceptron thing on the left, and then you have, maybe it's an energy landscape of a lookup into Mork somehow. It's just a pattern match, right? And so this gives us sort of another kind of modularity. Now, so what I've been focused on in my broader history, shall we say, is the continual learning problem. I've been wanting to figure out how to build a continual learning system. One of the most promising approaches I've seen for continual learning at scale in literature is this idea of modular continual learning. And so I'm going to focus a little bit on how do I build a PC transformer that learns continually? And the interim goal, and what I'm going to sort of focus on in this talk, is to give us some idea how you might build just a general purpose deep neural net that's modular, that learns continually, and has the right scaling properties. It's sublinear if the problem is sublinear. So here's what I mean by a modular continuous learning architecture. On the right, you've got kind of a high-level structure of the network. There are some defined modules. Each of these modules has some flow of information through it. The structure of a module is that there's some function. You can think that's one layer of a network, say, a neural network. And on the left, the internal, each of those modules has a set of parameters in a parameter library that it can choose from when it's presented with a particular task. So I won't go into some of the prior work and literature, but people have built these and demonstrated them, and they work pretty well. And the phases are, at inference time, the problem is to just select which of the parameters I need that's going to actually solve the problem. So find the best one. And then when you want to learn, you have to either update an existing set of parameters, or you have to, say, copy that set and update it so that you're not forgetting, right? And that's sort of the crux of the problem, is how do you do those three operations, that selection and that decision between updating or cloning? It's two processes. So we put together the generative attention mechanism that I spoke about a minute ago. And remember, it was a generative model that allowed us to have a rich enough signal to guide those local attention coefficients. It doesn't work in a discriminative mode, actually. The idea is, okay, well, if you have one of these modules and you've got a big set of parameters and you're trying to figure out which the best one is, well, you could just evaluate all of them and all the input, but that obviously doesn't scale because you want to have hundreds, thousands of these, whatever. So that's not going to work. But another idea is, well, let's just have some scope, some scope that's limited, and you can think of this as like short-term importance and long-term importance, like we were talking about earlier in the Hyperon setting. And then you can sort of traverse, you can sort of walk your way through the parameters with some other metric on how related they are, how good they might be for the particular task. And this allows you to have the PC inference steps themselves have a bounded amount of time for each of the module evaluations, but still traverse a potentially unbounded library of actual stored parameters. I'm going to generalize that one step further. I'm going to show you an example, so just bear with me for a second. So you take that architecture, and now you can actually say, well, what if these aren't attention coefficients anymore? What if this is just some context embedding that's being optimized by this local gradient in the local predictive error? Okay, well, the parameter source could now be a hypernetwork. It could be, some other kind of weird associative memory. It could be just a big vector database. Whatever you want. But it's going to have the same basic structure. So here's an example of what I'm talking about. So now we're back to, so zooming on that network I was talking about before, you've got some set of, some current best parameter, or this is really like the last thing that I processed, or my current state of the network. It had some parameter set that was like the winner for that step. But now the inputs have changed. Now it's time to do something else. There's some winning adjacent parameters. So we're going to evaluate all of these guys on the first step. We're not updating the parameters here, to be clear. In this example, you can think of each of these circles as one set of parameters in a vector database. So literally, this could be, one single weight matrix or one layer in a multi-layer perceptron, right? And they have some distance metric on them. It could just be the distance between the weights themselves. It could be the prediction error, based on the history of it being evaluated many times in the network, and there's other things you could do as well. So first time step, we evaluated the ones that are dark, and now we figured out that the best one is the red one, and it's shifted, and now there's a new set of next best ones, and then I'll do it again. Oh, now this one shifted, and now we've kind of walked our way through the graph. In typical PC update that's studying the literature, you might do 10 of these cycles or so. It doesn't take too big a stretch of imagination to substitute something like a hierarchical network of small worlds to do this traversal to something that's close to the best in log n time, actually, instead of this more linear thing. Okay, so put it all together. We're sort of now saying this network thing is a PC network. So these the arrows are now things that are predicting other things. The parameter source is now, we've taken that abstract thing, stuck it in a module. In the inference phase, every module evaluates and updates its attention scope and its predictions independently. And in the learning phase, every module also runs its update policy independently. So it's kind of just take a moment, like these modules don't have to be on the same continent, right? To Ben's point earlier, that everything's purely local. So this can be massively distributed. So what we've done, sort of unified the functional and structural paths into a single generative architecture. Structural paths is sort of a lingo if you look in the literature of this, and I can share some references if people want to dig into this. There's a paper called local module. I'm going to butcher the title, but it's a local module composition is the acronym for their system. And they have something that looks just like begging to be PCFI, because they have, the functional part of the module, and then they have another structural thing, and they use like a VAE for that. And it's like, well, PC generative models should just go in there. So this unifies those things. We're using this generative attention mechanism that I proposed to actually handle the sort of search, the selection process for which set of parameters we want in a given time. And then we've tackled the growth in the both inference cost and the memory growth, or we've tackled the growth, tackled the issue with the growth in the inference time cost with a concept of some secondary attention scopes, things that can be swapped out even to disk. And then we generalized this into support a wide variety of different parameter sources. Some possibilities for parameter sources, they could be simple things like just vanilla DC layers, just like Alex was talking about, prediction error, heuristics, kind of drive the phasing. So you do something very similar. That paper that Alex showed briefly with for his continual learning experiment was a big inspiration for this. So shout out to Alex for that. In the experiments that I've started doing this, I literally just copied his error spike heuristic. Basically what you do is to know when you want to clone a new module, you just look at the statistics of the prediction error. And when it spikes, then you're like, oh, it must be a novel situation. You have this intrinsic novelty signal that you can use to drive learning. You could do hypervector encoding as a parameter source. You could actually compress the library with hypernets. And you can also use, and this is particularly interesting to me, you can use some lower level continual learning mechanisms. So you can actually do things like, store many of these, or you can get a lot more leverage out of, let's put it this way, you can get a lot more leverage out of your weight update if you don't have to worry about that update being very prone to forgetting. So if you're using some mechanisms such as dynamic sparsity or structural plasticity, I think you can get a lot of leverage out of that. And I think when you synergize a bunch of these things together, you can actually get something that scales pretty darn well. So it's kind of our roadmap. Working on demonstrating that this is effective for, it's just some simple policies, simple vector databases, just to kind of kick the tires. I'm an experimentalist. I'm not an academic. I give myself about 3 days of notebook time maximum before I have to go write something, and then I learn more and go back to the notebook. So we want to verify that the learning and inference scale sublinearly with the number of tasks. That looks promising so far. And then the major question for me is whether the behavior when you have this attention process running on many modules, whether that converges well enough for real problems or not. And it's unclear to me whether that's the case. And then finally, as alluded to, some lower level continual learning mechanisms. And then the big prize is take what we learned from this and try to do a transformer. And I did pretty well on time, so I will leave it there.
Any questions? Yes. Can you come on up?
Come up.
Sorry. The microphone.
If we go back to the graph, you were showing a particular neighborhood as
Speak near this so they can hear you.
as you were going through, yes, this particular. Those are the operators. Are these similar to just basically activation functions, or these are tiny, basically subnetworks? What exactly?
Yeah, so they're really these guys. So they're these. So these are just different sets of parameters, which are options for each module to use to evaluate its function. And the idea is that when you want to continually learn, you want to add modules when you need to and reuse as many as you can when you don't, right? So this is a representation of how the traversal of those might work in the secondary attention scope mechanism, where I have a bunch of these, a bunch of these stored vectors. There could be hundreds or thousands of stored individual weight matrices parameterizing each one of those modules, right? I don't want to evaluate all of those at once, but I'll evaluate some based on, I've evaluated one, it was the best, it might be the best again, so I'll reevaluate that one, evaluate a few of its friends and a few of its enemies, maybe that are farther away, and then to kind of feel out where we should go in the graph.
And I guess my question was, how do you draw that boundary? Is that a graph and it's a Markov blanket?
Yeah. Well, it could be. But in this case, it's a policy. This is like one of the heuristic policy like parts of this. And if this was going to be a vector database of weight vectors, then that boundary would be drawn from some heuristics, potentially saying, well, let's look at the ones which have within the k nearest neighbors, say, in a cosine distance sense, or you could use other distance metrics, or you could look at the k nearest neighbors and then the k furthest neighbors to fan out through the graph and get coverage, because it might be that you're really close to the best solution for the current data point, but might also be really far away. You won't know that unless you try stuff that's distant.
And so in this case, some of them, they get inputs and they produce some outputs. And does it make sense to prune some of them out if you find that, for example, 3 of them, given the same inputs, basically produce almost identical outputs, even though they may be parameter-wise have a different structure?
So the way that I imagine that would be most effectively handled, and there's different ways to handle this, there could be post-process pruning. The way that I'm envisioning this for at least the initial test of this that's happened as a policy decision of when do I update versus when do I clone. And so if I'm getting the same results, I can just keep updating those parameters. I don't need to do anything else. And if I'm finding that I'm not getting good performance, then I have to copy something and sort of shift that around and leave the other stuff. So that's how I probably think about that. Another way is, as I was alluding to before, you don't necessarily want to take the k nearest neighbors. You want to take some that are distant, right? Because if you take the k nearest, it'll do exactly what you say, which is, sample things that are redundant, right? They may not matter. Like if your network is handling, it can read like Roman characters really well and kanji really well, it doesn't, if you're wrong in your guess and you're stuck on Roman characters trying to read kanji, no, you need to go far away and look at those. All the Roman character, parameter sets in here will actually give very similar kind of error values because they have the same kind of receptive fields roughly, whereas other characters won't. So you kind of have to do this. Again, a good model for this that I have is the hierarchical network of small world, where you have you take a couple different sample points in the graph and you traverse those and evaluate them to find, to get in the neighborhood pretty well.
So, do you have a GitHub repo or anything that I can run?
We are a little early for that, my friend.
Okay.
But I will.
And the final question is in terms of, is this something that will lead a way to self-organization in some way? In essence, you're basically going to be taking parts of network and building it up.
I mean, that's definitely the hope. So the idea is that, you give some overall topology that's hopefully roughly structured for your domain, but as you feed in, as these modules acquire different sets of parameters, that's going to influence what the other ones learn. And this is all guided by sort of what operations minimize the total free energy the most. So I fully expect that this will self-organize and you'll get stuff that, distributes properly through network. even accounting for if it's asynchronous, different processing time delays between nodes. Because if it takes long for a prediction to arrive from one section versus another, then that's going to be intrinsically less valuable, right? So there's a lot of interesting self-organization, self-distributing like dynamics that I would expect to happen here.
Thank you very much.
Absolutely. Thank you.
Thank you. Thank you very much.
Good. All right.
Uh,
That's what I think you're up next.
Yes, Beswick, please share with us about PC-based transformer information. And would you like to share your screen? I can see your screen, but I haven't heard you yet. What are you speaking? We can't hear you in the room. Oh, you're muted. There we go.
Hello, everyone.
Hello, we can hear you very nicely now. Thank you.
Okay, so my name is Bezai Tababa, and I will be presenting about the work we've been doing on predictive coding based transformers here in ICOB Labs, Ethiopia. So yeah, as we all know, AI is everywhere, and it's quietly embedded in almost every aspect of the modern life, shaping the way we work, learn, and even interact. And these AI tools that we now rely on so heavily are mostly built with the transformer architecture, and they have revolutionized the way machines process and understand information. And predictive coding transformer builds on this foundation, and it keeps the strings of the transformer, but rethinks the way it learns. And instead of relying solely on traditional training, it moves towards a process inspired by the human brain, and which is a predictive and adaptive learning approach. So yeah, the idea is to bring AI learning a little bit closer to how biological intelligence works. So what is predictive coding, or PC for short? Our brains are not just as passive receivers of information. They constantly make predictions about what they see, hear, or even feel next. So every moment, the brain is essentially guessing the future based on its past experience. And the clever part here is we don't really pay attention when everything works. Like we pay attention when reality doesn't match those predictions, and that error is what drives learning and adaptation. So PC applies the same principle to AI models, and instead of every parameters being updated from a single global error signals, it makes each layer predicts the activity of the layer below it in a top-down manner, and then update itself locally when it's wrong. So a little bit about the transformer architecture. It's basically an AI architecture that can learn the relationship between elements in a sequence, and whether those are words in a sentence or even pixels in an image, or so the key innovation here is the attention mechanism. So this allows the model to focus on the relevant parts of the input when making predictions. So here in the diagram, it's a decoder-based transformer architecture. And at the bottom, we have the tokens, which are the smallest units of the data. And these tokens are turned into token embeddings, which are the numerical representations of the model, the data, so that the model understands the tokens. And then positional encoding is added so that the model knows the order of these tokens. And that data is then passed into the decoder blocks, which consists of the masked self-attention layers and the feed-forward network, where the masked self-attention layer looks for the context of each tokens while blocking the future tokens. And the feed-forward network processes and transforms that information. So this process repeats for however many blocks we have. And finally, it's passed into the linear layer, which converts it into a probability for the next token, which is seen here at the top. So yeah, now that we have looked into the basics of the transformer and the predictive coding principles separately, let's bring them together. And the PC-based transformer combines the power of the transformer architecture with the predictive coding principles. And inside these architecture, instead of doing a single forward pass and backpropagating a global error, these models perform iterative inference, where each layers make their own predictions about the next layer's activity and not just based on the local errors. So, sorry. So yeah, it also adds lateral connection within each layers, which allows the neurons to influence each other in a way that encourages more diverse and less redundant representations. So for the learning, it pairs a local Hebbian rule for the weight updates at each layer and uses anti-Hebbian rules for the lateral connection so that the neurons don't all end up learning the same thing. And these predictive coding principles aren't just added to one part of the model. They are applied across all the transformer components, such as the embedding, attention, and the feed-forward layers. So here in the PC transformer block, the attention layer has 2 layers, and where the attention layer 1 predicts the activity of the attention layer 2, and based on that prediction, an error is computed between the target of the actual value of the next layer's activity and the prediction, and that error is used to update the weight of the attention layer 1 and also infer its latent state. And the same thing happens on all components and each layers simultaneously. So on our early results, we used these configurations to train the model on a small data set. And as shown here in the visualization, the plot shows a consistent decrease in the energy as the number of epochs increase, indicating the model is effectively learning. And the close alignment between the training and the validation energy suggests that the model generalizes well without significant overfitting. And this model, it's still being actively worked on and improved to achieve a better performance and an even lower energy levels. And with that, I conclude my presentation. Thank you everyone for listening.
Thank you very much, Bezawait. Are there any questions from the room? I think one of them.
I don't need to speak, just go back 2 slides.
Can you go back 2 slides?
Yeah, sure.
Previous.
Is this it? Or
Yes.
okay.
Just everybody's giving it a good hard look.
Okay.
Which test, which is this the words to speech, dependency grammar? Sorry.
One moment.
No worries.
Which experiment are you doing in TreeBank? What task are you doing in TreeBank?
It's a text generation. We tested it on a text generation.
Text generation. But is there a specific task?
I don't understand the question.
Are you doing a specific benchmark? Or are you just using the data set?
We're just using the data set to train
Yep.
the model for
Okay.
a text generation
Okay.
project.
All right. Okay. Thank you. Thanks.
Thanks.
You're welcome.
Any other questions from the room? All right, wonderful. Thank you very much, Bezawait. Thanks for staying with us for so long.
Thank you for having me.
Yes. And then I think we've just got one more section to wrap out the day. So Ben was going to talk about the potential extensions of PC, information geometry, algorithmic chemistry, perhaps open up a bunch of conversation.
So my role in this workshop seems to mostly be to talk about the speculative stuff that doesn't work at all yet and hasn't even been tried. But to be fair, a lot of the stuff other people have presented here corresponds to stuff I was thinking about 5, 10, or 20 years ago that at that point didn't work, had never been tried. And now a certain percent of it actually works now. Some things were tried along the way and quietly dropped as well because they didn't work. But so we've seen a few snapshots of progress toward hopefully getting predictive coding transformers to scale up. And let me say a little bit about how that fits into our overall sort of Hyperon-based AGI program before making a few comments on the more speculative things that Haley mentioned. So one way this could work operationally is we train predictive coding neural nets outside of Hyperon, nothing to do with atom space, and we have this large predictive coding transformer, once we get there, talk to the Hyperon atom space, right? And I mean, this could work for example, as I mentioned in the context of Andy's Questor presentation, like you pack into atom space a lot of knowledge in explicit logical form, programmatic form, right? Then when a question comes up that isn't encompassed in that knowledge, you ask the transformer, you get an answer. You can then take that answer, you can semantically parse it from natural language into logic. And we have Roman and Manhin in the audience here, and they're among the team working on using a mix of LLMs and some heuristics and PLN reasoning to get natural language into logic form that can be reasoned on in Hyperon by PLN and other methods, right? So then you have this big transformer neural net sort of sitting next to your Hyperon system, serving as a sort of a very knowledgeable but dodgy, occasionally hallucinating oracle, right? And I mean, you could also use a transformer to suggest proof sketches, right? Like saying, well, is this true? Give me an argument. It sketches an argument, and then you try to fill in the details of that argument with real logic or the more rigorous reasoning. And of course, proof checkers are being used that way with transformers right now, right? And then in that view, why do you want a PC transformer instead of a standard transformer? Well, it can be interactive in a much stronger sense because you don't have this distinction between reasoning phase and learning phase, right? So now it can still be interactive. I mean, if you took GPT-5 or Llama and had it talk to Hyperon, I mean, Hyperon can come up with stuff, pack it into a prompt and get an answer back. But if you have a PC transformer, then the stuff coming out of Hyperon can actually be used to drive real-time learning. It can update the weights of a little bit of the network in real time, right? And this can make interaction between a transformer or transformer-like network and Hyperon much more intensive. So now if you do that interaction, you only can deal with the sort of few-shot learning in activation space. You can't deal with modification of the weight matrix, which is weaker and has to be worked around in various hacky ways, as Daniel was describing, right? I mean, hacking around the lack of a really good long-term or working memory in transformers. I mean, I think that would end up making the neural-symbolic interaction a weird mess. You'd have to hack around it in bizarre ways. If you had a PC transformer that could update its weights based on what the logic engine was giving it, you get a much nicer neural-symbolic synergy, right? And that's the wimpy way to do it. We may well try that because why not? I'll be very happy if we get to try that by getting scaled up PC transformers. Now, the more interesting way to do it, I highlighted in my response to one of Connor's questions. The more interesting way to do it is, in essence, put the PC transformer in an atom space, not just by wrapping up standard neural net libraries in the atom space as a wrapper, which you can do already and call the neural space, but by implementing transformers in a way that, for example, leverages MORC effectively, right? So if you took either a waveformer or some other creative transformer architecture where the internal topology of the network mapped nicely onto MORC's internal prefix tree, and then you do the learning there on, could be multi-core CPU. I mean, there's ways to use a combination of GPU with multi-core CPU for this also. And we've had a whole bunch of discussions on, in general, how do you implement dense computational kernels against MORC, which, and we'll probably end up with a number of different approaches there. Then if you pay enough attention to the neural architecture and how it maps into MORC, and then how you execute that on your combination of processors, I mean, you may be able to get large-scale training of a PCA transformer to be faster in the MORC approach than it is in the current GPU approach, because there's a lot of intrinsic inefficiency in the way backprop is doing things. Like the synchrony introduces a lot of inefficiency. And as Alexei Polipov was pointing out, I mean, the inability of the intermediate layers to properly learn in the same way that the upper layers can do. I mean, these all introduce inefficiencies, right? And so there's a lot of efficiency you can have on the PC and more side, kind of playing a similar role, but maybe even better to the efficiencies you're getting from putting backprop on the whole like NVIDIA GPU library stack. And so that approach, of course, is more interesting. Because then when you have the PC transformer in the atom space, then linking it together with symbolic evolutionary attention allocation, with other sorts of learning happening in the atom space, this can be a much richer interconnection. And one suspects it would lead us more rapidly to something going beyond the transformer architecture. I mean, there's a lot to be inspired by with transformers. There's also a lot of other ways to do things, which you can introduce more recurrence into the network and neural symbolic links. And we've already thought about a lot of interesting things you can do there. I mean, for example, you could run pattern mining on the PC transformer network, right? And then patterns you identify in that neural net, I mean, you make a big symbolic library of those, and I mean, then you can include those, and you can include some activation spreading into the patterns mined from the transformer, stored in the atom space. You can include some activation spreading to that pattern library and back within the transformer's learning. And this becomes similar to things that were done in compressive transformers and other architectures following on to compressive transformers, where they were trying to keep a memory, which is sort of a compressed version of the transformer's memory state, but their compressed versions were vector embeddings, right? But you could do something like that with a compressed version, which is symbolic, formed from pattern mining on the transformer's state. So I think, having a separate PC transformer that can learn in real time together with a symbolic system will be a big step forward toward neural symbolic AI and potentially AGI. Putting the PC transformer in the atom space in the right way could potentially lead you even further, because you can get a much closer interoperation between the two sides. Now, there's a couple other extensions of the PC framework that I think could be interesting that would make this even more appealing. One of these is possible uses of information geometry, and uses of information geometry, the natural gradient for neural nets, have been published for decades, right? They've never been scaled up. The idea of information geometry is you replace the gradient descent with what's called the natural gradient descent. So you sort of, you view your neural net as a probability distribution in the space of probability distributions, and then you look at the shortest path through probability distribution space using the Fisher metric or the Wasserstein metric, or I mean other interesting choices, right? And you can then, in theory, you need a lot fewer steps to get to your solution. Now, that hasn't panned out in practice much, because the overhead cost of constructing this metric space among distributions and so on it's just been so much overhead that it ate up the savings that you get, basically. Like, it's fewer iterations, but each iteration is super expensive. I think there are ways to overcome that if you're operating at scale. Because if you're operating at a large scale, you can then train an estimator of the quantities involved in finding the shortest path in this metric. Once you have enough scale to train that estimator, then it may no longer be a lot of overhead. What's interesting then is you can do information geometry on a discrete atom space, like on the PLN network, and you can do information geometry on on the neural net, right? And you can look at shortest paths that span the symbolic and the neural part. And mathematically, it's all quite simple. Casting it out without huge overhead is another problem. But that's another example of what you could get by glomming the PC network into the atom space, because it just makes it simpler to construct a similar probability distribution manifold, because you can have the same probability distribution spanning the neural and symbolic part. Now, and I've written some stuff on this, which is on ArcSight. It goes into more detail. Another interesting thing I've thought about, it's actually where Daniel and I started when talking about this stuff, is you can do predictive coding discrete as well as continuous. Like, it doesn't just have to be for neural nets. You can take a bunch of discrete elements that are interoperating in some way to generate something or discriminate something, whatever you like. And the key notion of predictive coding, like you have some elements that are trying to predict what some element does, or trying to predict the error of what some element does. I mean, you can take that basic logic of predictive coding and you can use it on a set of discrete elements rather than continuous elements. I mean, then your continuous gradients are replaced by differences or something else, but the logic still works. And Daniel implemented some interesting prototypes of this a number of months ago, like enough to show that if you do it in a crude way, yes, predictive coding in a network of discrete learning elements can also work, right? And that's it was cool to see that prototype. What I started thinking is, okay, suppose you built, say, an algorithmic chemistry network, and this is a propitious place to discuss that, because the ERA cognitive architecture created by Kristen Thoresen from University of Reykjavik, who's our local conference chair. I mean, this basically is an algorithmic chemistry network, though they didn't call it that, right? I mean, ERA is a big bunch of rewrite rules that rewrite each other and then tries to self-organize into a state that can do something. And they got that to control humanoid robots and do a bunch of funky stuff in previous work. Now, what I would do in Hyperon isn't exactly ERA, but you could take a bunch of MeTTA rewrite rules and have them rewrite each other into other rewrite rules, and you have a sort of big recurrent soup of rewrite rules, rewriting rewrite rules. Then you have some of the rules write perceptual data into internal symbols, some of the rules write internal symbols into actions, and you can then try to coax this big rewrite rule network into doing stuff, which is it's the philosophy of Walter Fontana's algorithmic chemistry from the Jurassic period, right? And as well as what Chris Thoresen did with ERA in the humanoid robotics project. But none of them did it at enough scale, right? And you can go through the whole history of AI and you can see, okay, recurrent neural nets were done at shitty scale before. Like when I was teaching neural nets in the late 90s, I mean, we were doing recurrent backdrop on like 35 neurons in a network. It took 3 hours to converge on a Sun workstation, right? So, I mean, the idea wasn't terrible. It was interesting. We're just off by a large number of orders of magnitude from what would actually work well. Getting those larger number of orders of magnitude also made clear that recurrent backdrop sucks, and you want to be doing different things to scale backdrop up to big networks. Right now, you look at evolutionary learning. Harking back to my talk on Moses earlier, I mean, when we were doing evolutionary learning 20 years ago, we had David Goldberg's results on competent program evolution, and they included estimates on what your optimal population size should be for genetic algorithms for different problems. We were always like 3 orders of magnitude below those optimal population sizes, and we're just like, well, so be it, right? We'll do the best we can. So now, with Moses running in Mork, we should actually be able to run evolutionary program learning on suitable population sizes. Like you actually need hundreds of thousands to millions of programs rather than thousands of programs. And then you're getting toward what theoretically seems like it should be a big enough size given the objective functions that you're looking at, right? And I think the same thing may hold with algorithmic chemistry. I mean, when Fontana was doing it in the late 90s, early aughts, or even when Chris Thorson started out with this, I mean, 10 years ago or 15 years ago with Replicode and Era. I mean, you weren't doing it at a suitable scale, right? And we should be able to do algorithmic chemistry type stuff at a suitable scale with the infrastructure we have right now. It could be coded in minimal meta 2 against Mork right now. I mean, algorithmic chemistry is highly suitable for minimal meta 2. You don't need the full scope of meta for that. You then face the question, so how do we actually coax a network of rewrite rules to do something useful in the world? I mean, you don't necessarily have to try that hard. You could just try to get it to be mostly unsupervised and hope that clamping some of the inputs and outputs to useful things will propagate through the self-organizing network. On the other hand, it occurred to me, well, hold on, you could use predictive coding, right? So you have some of your rewrite rules, output stuff that's interpreted as predictions, and then you try to use predictive coding to propagate through the network. Have another rewrite rule rewarded if its output is a rule that outputs a correct prediction. Have another one rewarded if its output is a rule that outputs a rule that gives a correct prediction, right? And then you can propagate reward for correct prediction through the whole rewrite rule network. And for example, you could take a rewrite rule, you can attach with a number, which is like a chemical concentration or a weight, and you can just say, we'll nudge up the weight of rules that give correct predictions, or go all the way back through the chain of credit assignment, right? And in a way, that's simpler to implement than the PC neural nets, at least initially. I mean, there will be a whole bunch of tuning to experiment with there, no doubt. But coming to the point I started with, if you did that, it would be quite interesting to have a PC neural network in the atom space along with the PC algorithmic chemistry network. I mean, you don't have to. You could have the PC neural network outside, but then you can imagine like learn a shared probability distribution across the algorithmic chemistry river rule soup and the predictive coding neural network, use that shared probability distribution to drive natural gradient updates that are faster than straightforward gradient updates, right? So it seems like there's a bunch to do, but there's a fairly clear path here, right? So I mean, we need to get the just to crudely write down the neural and symbolic signs. I mean, we have more. We have MM2. We have the meta language, which is going into MeTTA IL, which then goes into Mork and into Rolang. So we have all these different components we heard about this morning. We then have distributed processing stuff like distributed atom space, and then the metacycle underlying the ASI chain, right? And all this stuff is going basically into a scalable atom space. And you know, this are done, and the other elements are Rolang is done. MeTTA IL and the DAS and metacycle are 1, 2, 3 months away from being done, depending on how much people's timelines slip. So we're pretty close to a scalable atom space. I mean, that doesn't mean there won't be bugs, and we'll still need to work on tooling of various sorts, but it's pretty close to there. Now, on the transformer side, we scaled up markers. On the transformer side, I mean, we've now we've replicated some stuff from the literature, and Bizawa didn't recount all the weird bugs and hacks she had to fix with that FISA's guidance to help get the stuff from the literature working in a reasonable way. But we're now playing with PC transformers, right? And we can then work in various ways on scaled up PC transformers. Then we can do that with improved memory and learning in various ways, which is what, for example, Daniel and Faza, among others, are working on, how to leverage the lateral connections better in other aspects to make memory and learning work better. And Faza has had some thoughts on sort of how do you change what predicts what inside the network when you're doing a PC transformer as opposed to a vision model or something. So there's a list of ideas being experimented with here, and then there's a path where after we've done that, we figure out a nice way to port that basically into Mork and into the scalable atom space. And then once these things are joined together, this is when we can experiment with a lot of quite interesting neural-symbolic synergy, right? And going along with, of course, what we're going to do on top of the scalable atom space is implement, or rather tweak and scale up and overhaul our current implementations of PLN, Moses, pattern mining, motivation, ECAN, and so forth. So we would seem like this piece, we're 1 or 2 months from having this stuff together. How long it takes to bang on all these things to make them leverage the scalable infrastructure is an experimental question, right? I mean, it could be months rather than years once we have scalable atom space to get to very, very interesting results, and probably some pieces will go faster than others. And I'm pretty optimistic about the pace here because the neural network, it's cutting edge conceptually, of course, but in terms of the tool set, you're using JAX and like standard tool sets that are quite common for playing around with neural nets. So like here, we're doing AGI research and building our own infrastructure concurrently. Over here, you're using standard infrastructure to do cutting edge research. So in some ways, it can go faster. And so we seem to have, during the next year or so, potential to get large scale neural-symbolic synergy working quite nicely. And of course, because of the metacycle infrastructure running on the infrastructure from Greg's Firefly team, and then feeding into the ASI chain blockchain that we're launching in a little later this year, assuming this does all work, we can roll it out on a decentralized network. So we have a quite different path to scaling than what's being done with big tech projects, which, because of business and technical aspects coinciding, really need to be run on like large server farms. I mean, the business aspect is these big companies that are making so much progress with LLMs, they have large server farms. They had them already, and they like the fact that only they have them, right? I mean, the technical aspect is if you have to do everything synchronously to train these big networks, then, I mean, you need big machines with a bunch of GPUs in the same machine. And if you have multiple machines, you need them to be right next to each other, right? So there's a confluence of business and technical requirements of a decentralized infrastructure. But neither on the PC side nor on the atom space side we have that requirement for big centralized infrastructure. I mean, of course, if you pack more processors in the same machine and put your machines right next to each other, things are faster than if you have a bunch of network overhead to deal with. But it's not as big a drop off as you get with these centralized, like backprop based architectures. So that's I mean, the reason I crammed all the Hyperon stuff into 60% of the day is, well, I don't think a PC transformer is soon to be an AGI either, even though PC is better than backprop. That's not to say some biological PC network can be an AGI, but we need a lot of other different components, right? I do think, I mean, there's a lesson to be learned from everything neural nets are doing right now, right? So thinking about the right way to get the neural-symbolic synergy to work at large scale is quite interesting. And that wraps up the workshop, except questions.
Hey, Ben.
Yeah.
As one of the people in the room, probably more focused on the business side than the science of this. You know, Eric Schmidt talked 2 weeks ago about tighter and tighter learning loops and context velocity. If we take what you've just explained, does this give us a differentiation? You know, tighter learning loops, increased context velocity, and so on, so we can say our models learn faster, they integrate, and then
Well, it really depends what, I mean, if you want to take a statement like that seriously, it depends on what you're learning, right? I mean, some things, you know, a very simple neural net can learn very, very fast, right? And I think the clear win you get from this sort of architecture is you get actual generalization out of distribution. And that's really the main point of AGI versus narrow AI. I mean, today's deep neural net based architectures are mainly, they're given a huge amount of training data and they can improvise a little bit beyond their training data. And I mean, Apple published a paper on this a couple months ago that got a bunch of press. I don't think, I mean, GPT-5 is cool. I've been playing with it. I don't think it fundamentally solves that problem when we see that Grok 4 outperforms it on the AGI ARC2 benchmark, which is more AGI-ish than the benchmarks that they've been advertising, right? So, I mean, that basic thing of being able to take a creative leap beyond your training data, I mean, that's the main thing that's added here. So saying learning faster is a little too generic, because I mean, if you're trying to use a robot arm to pick something up in the factory, it may be a narrow machine learning approach. Actually, it's fastest at learning to get that robot arm to move. It might be faster than me also, right? But being able to leap out of your training distributions is very interesting, right? And now for which tasks that gives a commercially better performance is somewhat TBD, right? I mean, many things may be better done by a narrow system. Like in economic terms, like our society has created job roles, most of which require very little general intelligence to do, which is part of why they're so mind-numbingly boring for the people doing them. And I mean, then maybe training a specialized system just to do that job is fine. And is the most energy efficient thing to do, given the way the jobs are carved up. I mean, Daniel, for example, worked for a while on speech processing aimed at automating the McDonald's drive-through. Now, that's not a super easy problem because people say a bunch of dumb shit coming into the McDonald's drive-through, right? It's still not obvious that really needs an AGI versus just a well-tuned narrow AI system, right? I mean, there's not that many AGI hard queries coming into the McDonald's drive-through microphone. So it's sort of an open question for which things having an AGI is a more economically or computationally efficient approach than having a narrow system. I could tell you some applications that clearly need an AGI though, which not coincidentally are ones that we're working on, right? I mean, certainly in the financial markets, if everyone else has a narrow AI, you have an AGI, you'll be able to find ways to win, right? I mean, your AGI can work with the narrow AI. It can use it, but it can see something else. And as we get near the singularity, there's more and more regime shifts in the market faster and faster, which means that narrow AIs will do worse and worse because they're always trained for something different than what the world is bringing. In scientific research, for example, biology research, like Mike briefly alluded to, or the research in various domains that the Quest or research assistant would do. Scientific research by its nature is about leaping beyond what's known, right? So there you clearly need an AGI also. I mean, I would say business strategy, when it's really that and not just bullshit, I mean, is also that, right? Because you're dealing with regime changes in even more nebulous sense than in finance. I mean, like to try to run a tech startup now, you're leaping into the wild unknown like every day. The world is always changing, and the model based on the prior distribution will not be good enough, right? So I mean, creative art is the same way, like making art or music that isn't retreading and plagiaristic recycling of what came before. I mean, that also requires taking a leap beyond the training data, right? I mean, that's like Ozzy Osbourne recently passed away, but when Black Sabbath wrote War Pigs, like that was a leap beyond the training data, right? That was different. And to make that sort of leap certainly requires something more like this than like transformer neural nets. So I mean, in some cases it will result in learning faster, but that becomes particular. Yeah, go ahead.
I want to play devil's advocate for a minute. Before you do that, just to connect back to what you were saying. A little tiny equation like U equals MC squared resulted in a leap beyond the training data to use this break. It changed the entire regime, right? It changed the way nation states were organized. Right? So small, tiny changes like that make big differences. But that goes back to how I want to play devil's advocate here. All the talks here are very cool. They're very exciting. And at the same time, it feels to me a little bit like a tail wagging the dog, in the sense that the architecture is driving, is behind the driver's wheel, as opposed to, a small little equation like.
What do you mean the architecture? You mean the cognitive architecture, or you mean the software architecture?
What I would love to see is an algebra sense making. A nice, simple, compelling story about how sense making, a sense making apparatus is compositional and enjoys certain laws that we can write down on, say, half a page, at most a page. Right, that to me would feel like it has the right characteristics.
So I have two reactions to that. One is it's a perfect setup for my keynote on quantile weakness today, which is an attempt to make a beautiful algebra Occam's razor heuristics that can be applied across PLN, Moses, Eken, and all these different mechanisms. So I somewhat share that instinct, which is why I was psyched to figure out that if you generalize Bennett's notion of weakness to quantiles, you come up with the right measure of simplicity. It gives you SVM margin, it gives you probabilistic learning, it gives you quantum learning, it gives you things about PLN. So I think you can go a bit in that direction. I also, however, studied enough biology to be wary of physics envy. And I think physics is like that. We know that. You have E equals MC squared. I mean, you also have the standard model, which is ugly. I mean, it's you could write it on a t-shirt in small print, but it's not E equals MC squared or general relativity, right? And it is still the best physics explanation we have of most of the little particles going on. But I would say I mean, we've all read the stories of when Feynman tried to study biology and then gave up because it was just too messy and ugly. He decided to go back to basically looking for the money where the light was shining, right? So I think that's a worthwhile quest, which underlies my attempt to find an Occam's razor heuristic that can guide all our different algorithms in a unified way. On the other hand, I would also say like AXE is very elegant, Gödel machine is very elegant. Like if you eliminate resource restriction, and I'll give a different version of universal AI that's even more elegant than my talk on weakness. So if you get rid of resource restrictions, you do have beautiful equations for learning. I mean, Marcus Hutter's equations in his book Universal AI are quite nice. My equations on weakness-based universal AI are nice. Like if you get rid of scarcity of energetic space and time resources, you do get nice, elegant equations for what general intelligence is like. And you can look at the human mind, sort of like the human body. It's a specific adaptation to a specific and nasty collection of resource restrictions, right? And so then you're asking like, what's the general theory of walking? What's the general theory of reaching and grasping, right? I mean, there's physics, and then there's specific constraints on how these limbs are working, right? So you could look at human intelligence and human cognitive architectures a little bit like that. Like we evolve with some specific constraints, and then things like, you know, how declarative and procedural memory interact and how working memory and long-term memory interact are just the best hacks that evolution came up with to respond to these constraints. So then when you're building a specific AGI system with specific resource constraints, and especially if you consider like now we may barely have enough resources to make a human level AGI. I mean, we may not even, but suppose we do, then we barely do, right? So then you're hacking pretty hard around the resource constraints. So I guess the question is, like, what is there in between these very elegant abstract theories of intelligence that ignore resource constraints and just hacking something that will work on the exact resources that you have? Like, how do you make a bridge between those two levels? And that's hard. Like I consider as a rough analogy, no one has a theoretical derivation of this thing from quantum mechanics, this periodic table of elements. Like you get about here, right? You don't get here yet to helium even with theory, right? With simulation, I think maybe they can get to helium now, but not much further yet with simulations, right? Like we know the one follows from the other, but we don't bridge the two levels analytically yet, which is annoying, right? But so we're kind of trying to do something like that. We're trying to get from fundamental theory of universal AI to the hacks that work on current computers, and we're trying to bridge the very elegant but impossible with the feasible but ugly, and find like a nice theoretical bridge between them. So I mean, what amused me with this weakness stuff is that to some extent it gives a way to do that. And yeah, maybe there's a thorough way to do that. On the other hand, then you have the choice like stop building and do theory, hoping you find a really elegant way to guide what you're building.
Well, I don't think you have to.
Because I mean, LLMs are doing a lot of shit, and they're not theoretically grounded very well at all, but they're doing a lot of cool shit.
Well, for example, makes me more scale is that there's an algebraic structure underneath.
Sure.
Right. That's why it scales. And similarly, one of the most interesting things about the mobile process calculator is that they do have this fascinating paradigm of linear, nonlinear, and the way they're joined together.
Sure.
Like in Rho, the parallel composition operator is linear. It is all about resources. Whereas when you send information, the information that's received is copy of it. You have linear and nonlinear combined in a very interesting.
I understand, but you could say that database and programming language envy is in the same context as physics envy. Like these are not AI, they're different sorts of things, right? I mean, databases have a nice relational algebra. I mean, many programming languages have nice math foundation, and AI has just tended to be messier. And so, I mean, you know, the good old neat versus scruffy dichotomy in AI, right? So that historically the neats in AI wanted everything to be nicely mathematically organized and grounded. The scruffies in AI were like, let's hack shit and train and get it to work. So the scruffies are winning, right? And the scruffies are winning by a lot. And I mean, I'm pretty scruffy, right? But I have the liking for this sort of mathematical elegance. I just have a worry that it's not, that AGI has to be more like a messy biological natural system. It's hard to capture in that elegant way. So, because databases and programming languages are more controlled, simple domains in a way. That the thing with AI is, I remember when I studied numerical analysis, was what I did my PhD in. You had nice theorems about the algorithms, but in practice, the algorithms everyone uses always converged much faster than the theory gave you any reason to believe. It was just sort of lore. And that probably had to do with the way the details of the algorithm connect with the type of problems that we ever care about feeding them. But no one ever sorted that out. It was just people knew, well, okay, we have nice results about these 10 things, but only ever use these two, right? Or for this kind of problem, only ever use that one. So like even with numerical analysis, it came down to lore. Yeah, but my point is AI is the same way, and transformers are the same way. It's just been a lot of stuff seemed to make sense. People tried a lot of things. Some of them worked really well, and we haven't ever managed to eliminate that aspect from. It's same like with different kinds of crossover in genetic algorithms. Like why do you always use some and not the other? Because they work, right? So we haven't managed to get rid of that aspect, right? But it is interesting to try.
Well, I wouldn't have said anything if I didn't have to throw in.
Yeah, sure.
We are.
Well, we can do another couple questions anyway. Oh yeah, no, I'm not going.
Well, then that's.
Right, okay. Yeah.
You're going to skip the show.
It's actually here. Yeah. So.
All right.
I can pay more of that.
Like an interesting thing that's been popping into me is the research I've been looking.
The what research?
Research is these things are stuff trading for compute, right? And that maybe there could be an interesting crossover because you have a biological substrate that can be quite messy, tracing out, but you can apply other principles to that, within a computational format and get some interesting results. And economies you can compute while you're at it. Maybe, I don't know, just reminding me of that.
I mean, that's a whole other area of research, which is interesting. I hope we don't need that to build an AGI with Hyperon.
Do you know explanatory powers? Yeah. Borrow from life to get it.
Well, but you can study those organized way better than you can study what's in the brain, right? So, I mean, if you did train brain organized to do a smart thing, be it AGI or a specific smart thing, you can make a whole lot of electrodes on there. And actually, the cost of setting up a brain organized is mostly the electrodes to measure it rather than the organoid to actually do its thing. So, I mean, it's very interesting in terms of Aurobia's talk, in terms of understanding what kind of predictive coding or what else the brain actually does, right? I mean, getting a brain organoid to predict something and seeing if it's doing predictive coding based propagation inside the organoid is an experiment that can be done right now. Like training the organoid to do stuff and trying to measure and learn what the actual learning algorithm is. So that would be super interesting. And who's to say you don't learn something from it that helps make better computer science learning algorithms too, right? So I mean, it's all very cool. I'm thinking we don't have to go there, but I'm happy for someone to go there. Yeah.
So I don't know if people have heard about this example, but a lot of the major LLMs had this particular form of